Live. So today is basically just going to be modeling a whole bunch of stuff. The first thing I want to model is I just got this stepper motor, and I've imported it from Stepper Online's documentation. And now what we're going to do is just build a little hat for this thing that goes around this thing, because the servos that I was using for this face tracker I was building, it has a screw on here. So if we just undo this, because this is not necessary. There's a screw hole in this face of its thing, and it doesn't have a notch here, but it is geared, so you can put this little hat on it. And so I just need to redesign, because the stepper motor it just feels way better. The servo, it's like creaking and cranking, and it just sounds like shit. This one, it makes sound, but it's not as jarring. Plus, I want to get to know to use stepper motors. So what we need to do, actually, is we need to go back and do this. Is that still offset? So we need to take this and this. We need to offset it by... We want the width of the walls to probably be 2 millimeters. So let's just say 2.2. Okay. But, oh wait, but we also want to... let's try this. What the hell is going on? We have this, this, and this. If we try to offset this by 2.2, does it do what I want? No, yeah, that's so weird. Oh, there you go. Okay. So yeah, so we have this. So this is kind of the face that we want. And then I want to make all this construction geometry. With the X key. This X. Okay. So now here we're going to extrude this by 2. 2 is probably thick enough. Okay, now I actually want to build it downward, but so I want to draw on this face, and I guess I gotta hide this thing. Can I still? Okay, nice. So I can still have that. So which is the real one? This is the real one. So what we want is we want to now offset this by 0.2. What am I looking? Or not from? Oh wait, can I just project this all into my? Okay, so now I should be able to. Oh wait. Whatever. So I should be able to, yeah, select this, this, and offset that. Damn it, what the hell? Should I just redraw it? Alright, let's just redraw it. L dot make it a... Okay, so if I do this... Oh wait, but I don't want that. Yeah. Okay, well what if I just try it? Could not offset curves. What the hell? Wait, what if I just try this? Wait, that's weird. No, but I don't want that part of the arc. Okay, wait, that's that. Okay, so we're good. So now if I offset, dude, what? What the fuck? Wait, what if I just, wait, oh, okay, wait, hold on. Wait, if we hide, wait, is this the current sketch? Okay, so let's, oh wait, maybe that's the key. There's like 2 there. That's probably what's going wrong. Oh, okay, cool. So now if we do -2, maybe we should do -2.1. We really want this to be tight because I don't want this to slip at all. So hopefully 0.1, that means 0.05 clearance all around. Could be fine. Okay, so now this so wait, hold on. I thought I did new body. I guess I forgot to do new body. Okay, but effectively, yeah, we want to extrude this geometry by, what, 7? No, like 16. I don't want to do 2 face. Does it calculate the distance? Maybe I could just do inspect. From there to there is 24, so maybe I could do 22. Oh, wait, no, but I don't want to do that because if we look at the geometry of this notch is going to collide. So we actually want to know the distance from this face to this face, which is 15. So I say let's just do it to 14. I'll just do 14, I guess. Okay. Or whatever, we'll make it 15. Okay, so yeah, so let's extrude this by 15. And you would hope that it tells me that there's some interference. But I guess since it's the same body, they're not going to tell me that. Okay, but then I just want to draw a little thing on here. Oh, I guess I want to draw it from this side. So how do you do that? Oh, maybe I can just do that. Okay, so we do new sketch. And we want to do it on, yeah, but not on that face. Where's the origin? Let's hide the body. Hide the body. Oh, see, but that made a new. I don't like that. We'll start this over. That's how these things go. Okay, so we put it on that, but now we need to offset it to the mid. Oh wait, this is the middle. That's pretty nice actually. So now we just need to draw a line. We'll just extrude a rectangle. Oh, you know what? I probably could have just drawn a rectangle on it and extruded it. I don't need it to be a triangle. Alright, so let's cancel that. If I just extrude this, I think it just works. Okay, cool. Alright, so now we have done it, and we should be able to put this on. And I mean, ideally, I could, like, do the experiment to figure out how much force it's going to take for it to slip. But for right now, I just want to start small, because there's a lot of stuff to model today. Okay, so we're just going to do this all over again. Okay. So I'm going to do assemble, new component, hat. Oh, and the parent is this. Oh, wait. I wanted to actually import this as its own component, though. Oh, I think that, okay, that's fine. Yeah. So now, oh, and there's actually this taper here. I didn't, so the distance from here to here is 15, but what's the distance to, does it tell me, oh, it does tell me both dimensions. So it's 0.5 millimeter. So yeah, I think I'll just make it a cylinder. I don't think I actually care. Okay, so we are gonna. Okay, so we're gonna do a new sketch on here. Then we need to project this stuff and make them all construction lines. Do we need this? I guess I'll do this. And then what is that one? Okay, so then that should be all I need. Oh, and then is that curved or does that just look curved? I don't think that's curved. Okay. Okay. So now we offset. Shit. This, that. And we want to offset this by, what did I say? 2 point, I guess 2.1. Okay, and then this is getting like really, okay, there we go. That's way cleaner to look at. Oh, and then this is not a construction line. This is a real line. Same with this. Okay, then we want to take this and offset it again by -2. Oh, what? One or more of the selected curves has already been offset. Consider offsetting the original profile. Oh, that's interesting. Oh, and you know what? Wait, did I fuck this up? First, we want to extrude this by 2. And then where's the body? Okay. So yeah, then we want to draw on this face. And we still want to see that other sketch. Where's those sketches? Is it this? Okay. So now we want to draw on this face. Okay. So now we want to. I don't think it's gonna let me use this because it's part of another thing. What if I just try to project it? Okay, whatever. Okay, yeah, that should be good. So now, hold on. What the hell is going on here? Why can't I select just the part that I want? First off, these are all supposed to be construction lines. Fuck. Why can't I do what I want? Oh, come on, man. What the fuck is going on? Because if I try to extrude this... Oh, wait. What the hell? Is that why? Oh, wait, no. That is... No, that's not what I want. Because I need... What if we just did that? Why is this so high up, though? Okay, well, I don't know exactly what happened, but that's... No, wait, but that's the opposite of what we want. We want this face. So cancel that. Why is this up there? That's the weird part. Okay, wait, if we do this... Let's just finish the sketch. Okay. Maybe I have to project more geometry. Okay, so let's try to draw this thing. What? I feel like it's selecting the wrong thing for me to draw on. Oh, no, it's not. So I do want to hide this. And then I want to hide that, whatever that is. But oh, wait, what if I did this? Hide this body, enable that, and then wherever that guy is. Is this the expanded one, though? Is this the big one? I don't think so. So wait, so let's just project this, this. Okay, so now we should actually... I don't know how to select this thing. Oh wait, maybe we need a line here. Wait, but we need a line... Oh wait. Bro, why is this tweaking me out? We have this like closed curve here. Well, actually, okay, you know what I can do? I can just extrude this by, what was it, 15? Okay, let's do that. But then hide this, and then we want to take this, and we want to extrude that minus 15. And we want it to cut. Okay, so at least we got it. Okay, so that should be good. Now we just need to extrude this face by whatever, 15. How much was it? 20. No, let's just make it 20. No, why do we need to do that? This is just to see if it works. Alright, 20 is fine. So now this body hat I'm going to save as mesh. Hold on. We're going to call it stepper hat. Okay. So now that I have the mesh of that, I can go to Bamboo Studio. And oh shit, I forgot. I keep having this issue where I'm sure other people run into this. I don't know why. If I print with the white filament that I have, here, I'll show you when I get into the Bamboo Studio. It's so random. I get this error on the last layer. The print is like totally done, but for some reason, but it's only with this orange. If I do it with this white, it works totally fine. So I forget, what is the fix for this? I need to remember. I think what I do is I disconnect the PFTE tube on the back. I pull it out, I cut some out, and then what? All right. I guess I'll be back in a minute because I can't print this thing until I fix this thing. But it's so annoying because I can't print with orange without having to deal with this. Presumably. What the frick? That's actually kind of annoying. In some ways, this is the first time I've exported as 3MF, and it's actually more annoying to use 3MF. Okay, so that's good, and I mean, yeah, that's totally fine. This should only take like, yeah. And then maybe later I'll bring out my stepper motor and I'll show you guys. Because I got it working. It's kind of inside and it's all... But maybe it'd be good to show how it works. That code is total garbage, but whatever. It uses a potentiometer and it just like spins in the direction of the potentiometer. Okay, let me go fix this bullshit. I really hope it's not the AMS that's messed up. I really hope it was just that orange. I don't know. It's weird. So I would hate to not be able to use that thing. Anyway, so I've never replaced this filament. So on the wide piece, okay. So I have my filament. Damn, this is really sealed. Okay, I need to get some scissors. Okay. Alright. Oh shit. These silica beads. Hey, I don't think I think it must have broken transport or something. I have to clean those up. Okay. Okay. Okay, that piece needs to go to the block. Okay. Oh yeah, so I put it in backwards. So hold on. Where's the end? Here's the end. So it should go like, well maybe, okay. Alright, there's only a notch on one side, so it can't be that. Did I get it? I can't tell. I must have. Okay. Align it with the notch on the inner ring of the filament roll. Insert the wide piece into the filament roll. Align the triangles. Align the triangles on the rim of each piece and insert the narrow piece into those. Push firmly into the wide piece. Okay. It just keeps coming out though. Okay, that seems strong. Okay, then you just pull these guys. Okay, this is whack. Oh, I need it. Oh, I need that paper. Stick the included label into the groove. Oh, yeah. Well, it is PLA basic, so that's fine. We don't need to do it. Okay, so now oh, there's one more. So now I can go install this, and hopefully I can print a black part. Okay, so yeah, this desiccant like just completely just exploded in the bag. Okay. I'll be back. All right. So now if I sync, that's not right. Oh, there we go. There we go. Okay. So now, slice plate. Oh wait, I didn't get to do color picking. Okay. So that's our little modeling test. So yeah, I guess in 12 minutes we'll figure out whether or not I actually have a problem with my AMS. Oh yeah, that reminds me, I need to clean up. The bottom of the bed is like totally gross. Okay. So that's one thing. Now the next thing is a rack and pinion. So right, so instead of a so I think the first part is I'm just going to follow these two tutorials. But then after that, I'm going to adjust the design so that I can put a servo in there and design a little program for the servo. And then I don't know how you're going to create a low friction interface between the rack and the ground. But maybe that's not important. See, this is a nice design because you don't really need a handle or anything. It's pretty minimal components. Oh wait, maybe I should this.
And
Okay.
also highly educational. Let's jump right in. We'll begin by creating a new design, and here instead of starting with a sketch, we're going to go ahead and start by using a gear generator right under the utilities menu here, and we can go to add-ins and then script and add-ins. We'll get this dialog box, and if you scroll all the way down, we'll see our Python spur gear generator. We're going to click run, and you'll get the
Okay. Yeah, so let's just start a new one.
dialog box here. Now, don't be overwhelmed if you see all these terms here that you may not grasp the full meaning of. I'm no mechanical engineer here, and actually my approach to this was just to kind of play around with the numbers and see what happens, sort of a trial and error here. So the way I started is I looked at this pitch diameter, and I have a pitch diameter in mind of the size of gear I want to make. So I started experimenting with the numbers here to see what effects that parameter there. Now you can't directly change pitch diameter, you just can only affect it by changing these other parameters. And I found that the two that affect it are the number of teeth and the module. So number of teeth, 24 sounded good to me. Module, I brought that down to 2, and that went from a 300 and something pitch diameter to 48 millimeters. All right, that looks good, except I've got this sort of message here, and I can see my OK button is grayed out. So let's look at what that message says. It says the root fillet radius is too large. It must be less than 1.18. No problem. I can make that happen. Root fillet radius, going to change that to 1. Now, the rest, the gear thing.
Okay. Okay, nice. And so presumably I can just make the, can we do that again? Hole diameter. Yeah, so what was the hole diameter? Five. Okay. But yeah, that should be fine.
Thickness, you can make that whatever thickness you want. I'm going to leave it at 12.7. Not sure if that's sort of a default gear thickness or what. Hole diameter, I'll just leave it the same as well. You can always change this by creating a sketch and extruding anyway, but I'm going to not complicate things, leave everything else as is, and click OK. And there we have it, my gear right there on the origin there, centered on the XY plane in this orientation.
Did that automatically make him a new component? Oh yeah. How come his is orange, man? I want mine to be orange. Oh wait, maybe it's just this. If I like right click this thing, can I appearance? Yeah, appearance, but also maybe that's like deprecated? I don't know. Oh, I have to drag it on here. Okay, that was stupid. I don't want that. Why can't I right click this thing? What the fuck is going on? There we go. Yeah. I want mine to be
if
orange.
I want, but I'm just going to leave it as is. And you also, one thing I want to point out is that came in as a component. So you can see the little component symbol there. And if I expand it, you see you've got your own bodies and your own sketches. And the cool thing here, if I go down to the timeline and I click the little plus button, you can actually see how this component was made with that Python script. So here, if I just walk through the timeline, we've got a couple sketches there, an extrusion, a second sketch here, and this sketch actually shows the profile that was made to create the tooth of the gear. So here we see it's generating a bunch of spline points to create that profile, and then the next item here is it extrudes it up, and we have a fillet and a circular pattern. And then
that's actually nice to know.
Final sketch here shows
the Python API must be pretty
pitch diameter circle
nice.
Here at 48 millimeters. So I just wanted to show that here just in case you were curious of how they made this and you kind of wanted to see an approach on making your own. Okay, that's that. I'll collapse that timeline there. And now we'll create our next component here, which is going to be our rack. To do that, I'll click on the top of my browser here, select new component, and give it a name. We're going to call this one rack. And then we're going to orient to a top view here as we're looking at it from our view cube orientation. And I'm going to right click, go to move copy. I'm going to select the translate option here. Move object is set to bodies. I'm going to select the body. And I want to move this down a certain distance. Now, how far do I want to move it down? Well, this is very important because this is what's going to determine whether the two gears mesh, or in this case, the gear in my rack. So the answer to that is you want to look at what that pitch diameter circle is here. Let me cancel out of the move copy for a second. And it's very faint, but if we have it turned on, even though that component is not active, we're in the rack component, you can see it right there. And click on it, it's that dashed line here, and we can see the diameter is 48 millimeters. All right, so that tells us that we want to move down 48 millimeters, because anytime you have two different gears, no matter the sizes, as long as you get that pitch diameter circle to be tangent, the gears will mesh. So again, I'll pull up my move copy by right clicking. I'm going to change this move object to bodies. Selection is going to be my body here, and I'm going to choose the translate option. Create copy. I'm going to make sure that's activated or enabled, and I'm going to move this down. I can just go ahead and type it in right here, negative 48 millimeters, and I'm going to click OK. Now I'm going to go back to that spur gear here. I'm going to activate that component, and I'm just going to rotate this so that it looks correct. The important thing here is that this bottom gear, that this tooth over here is going to be facing straight up. But just so that it looks right, I'm going to right click, go to move copy, and I can rotate this by clicking on the body here. Make sure I have body selected. My move type is going to be rotate, axis rotation. I can select any one of these circles here. I'll go with that inner circle, and now I can start moving this to give me a rotation. Now I can eyeball it, but you don't really want to do that. You want to be as precise as you can get. Like I can see that kind of works. So we want the exact number here. And how do we figure that out? Let's back up for a minute. And I'm going to explain this because to me, this is something I find really helpful. So I'm going to go under the assumption that you may find it helpful as well. Now, you may be a math whiz, but not all of us are, and I'm certainly not one of them. So I have to kind of think of the rational steps to slowly step my mind through how I can approach this, and so that it makes sense, versus just like, oh, what's the formula to do this? Because I find memorization to be useless. Okay, so the question I need to answer is, what is the precise angle I need to move this? And the great thing with Fusion 360, even if you're not kind of sure of the math,
you probably want to do 360 over 24 over 2. That's my guess. 360 over 24. Okay, so I think you're supposed to move it 7.5.
Figure it out by measuring.
Wait, let's do this thing. Okay, so now here, new component, rack city B. Okay, now we want to move this thing. Bodies, this, whoa. Top, right? Is that what he did? Yeah. Okay, now we want to move this down minus 48. Oh, and we want to create copy. Okay, then we want to rotate this thing. That's not what I wanted. Oh, wait. Okay, so we want this thing. I'm going to move it. I'm going to rotate it. How do I pick an axis? How did he pick an axis?
So let's go ahead and create a sketch.
Oh,
now here I have the spur gear component activated, and I'm going to create a sketch on that surface of that gear. And so basically what I want to know is, what's the angle to move this gear one tooth over?
Oh, am I?
All right, so what I can do is project in 2 points. I'm going to hit P for project, specified entities is selected, and I'm going to click on 2 corresponding points on different teeth. So this point right here, if this tooth is moved all the way over one step, it would be this same point here. I'm going to click OK. And I'm going to draw a line from the center origin here to that first point, and then draw another line to that second point. And if I hit D for dimension, I can click on both lines, and I can see that that is 15 degrees. Perfect. That's all I needed there. And the other way, if you just want to use math to do this, you can say, well, okay, if I take 360 degrees, which is a full rotation here, and I divide it by the number of teeth, that should get me that same angle, right? Because you take that angle times it by the number of teeth. Perfect. The overwhelming of the problem. And fine if you just the homework right there. I'm going to choose the rotate option, select that inner circle, and I can start twisting it. Now remember, 15 degrees, if I do 15 degrees here, it's going to go one full rotation, which is really not going to help me. I have to take half of that to get it to go in between the two teeth there. So half of 15 is 7.5, and enter. And there we have it. Okay, a valid question here would be, wouldn't I want a little clearance here between the teeth so they're not, grinding? Yeah, you can do that. So instead of moving this 48, maybe I would move it down 48.2 millimeters, give me a slight clearance. But to be honest, I was curious and just tried printing it out with no clearance, and it worked fine. The gears weren't getting stuck or grinding. So I'm just going to keep it as is here. But remember, you always have the option, if you need to space that down a little more, to give it a little more clearance. And I'll probably start with like 0.2 millimeters. Okay, I think I'm going to stop there for now. I can see that a full tutorial of the entire assembly is going to take quite a bit longer than I anticipated. So instead of making one really long video, I think I'll go ahead and break this down into a multi-part series. So next week we'll look at creating or jumping into that bottom gear there, that bottom spur gear, and we're going to isolate this one tooth here. It's the only one that's facing vertical, right? So we'll look at isolating it and creating a rectangular pattern of it so that we can create our rack here, and also talk about the math involved to get the spacing just right. So stay tuned for that. I'll upload that video in a few days.
Cool. Please don't be a part 3.
Hey guys,
Oh
Vladimir
my
here with
gosh.
Desktop Makes. I want to pick up where we left off, where we are looking to create this rack and pinion assembly here. So let's go ahead and jump right in. If you haven't seen
It
the
does
first
look
video,
sick
just go ahead
though.
and check out my videos. It will be the one right before this one. Okay, so we created these two spur gears here, and the bottom one, we want to go ahead and take that and convert it into a rack. We'll go ahead and activate the rack component, and I'm going to create a sketch on this bottom gear here. And what we're going to do is just project the outline of a single tooth. And now here it's important that this one tooth is facing completely vertical. So I'll hit P for project, and I have specified entities here selected, and I'm just going to click on the outline here. Just be careful. You do have to make sure you get the line. If you accidentally click on the inside, just click again to deselect it. And we're going to select these curves here. And then once you get your selection, go ahead and untoggle the body here. And you should see the outline there. That looks good. And then we're going to hit L for line and just connect these two bottom points. Now you can see here we have the purple outline, but it's not connecting because we can't get like a profile. This is what it looks like when we click on it. It should be highlighted blue. And I can tell if I zoom in here, I can see that it's because we have a gap here. Now a couple ways we can go about addressing this. We can just hit L for line and connecting these two lines. You know, you're perfectly fine just doing a line there. That length is 0.026 millimeters, so it's not going to affect it, especially since we're 3D printing this. But another way you can address it is just clicking on it, hitting delete, and then we can come in with a tangent arc. So under the create menu arc, we'll grab a tangent arc, and then I can click on this top point and then click on the bottom. You can see it automatically adds the tangency, and we'll be good. Now if I hit D for dimension and inspect this arc, that's 1.028, and this one over here is a straight 1. So it's not perfect, but again, at the scale here, we'll be fine. So in fact, I'm just going to do the same thing for this one, just so that they're both even. I'm going to go ahead and delete that. I grab my tangent arc here, and we'll go ahead and click on that top point and on that bottom point. Now you can see if I click on it, it highlights blue, so therefore I know it's a closed profile. So one important takeaway from here is when you do bring in geometry, either as an SVG or DXF, or from projecting geometry and it doesn't highlight, you probably have an open connection there. And so zooming in to where these endpoints meet is a way to figure out where you need to address. All right, so we have what we need. I'm going to click Finish Sketch here. Then I'll hit E for Extrude, grab my profile, and I'm going to change the extent type to object, and I'm going to orbit to the back of the gear here, select it, and it'll reference that as a distance. I'll click OK, and there goes my one tooth
Pretty
there.
nice.
I don't need to see the top spur gear there, so I'm going to untoggle the visibility. And within my rack component here, I can see I have two bodies. Body 1 here, which I don't need anymore. That was simply to reference that, that top tooth there to extrude it. So I'm going to right click on it and go down to remove. This will keep things a bit simpler. Okay, now we're going to take this one tooth and do a pattern of it. So let me untoggle sketches. We'll go to a front view. And I'll grab my rectangular pattern tool under the create menu, go down to pattern, rectangular pattern tool. So here we're going to choose object type as bodies, and we'll select our body. For our axis here, we're going to select the bottom edge. That tells it the direction we want to go. And I'll just grab this arrow and start bringing it out. Now, a couple important things we're going to want to do here is change the distribution type to spacing and the direction from one direction to symmetric. Now we have to figure out the distance, and this is the distance between teeth here. So if you recall from the last video, we had to figure out the angle between teeth on the circular spur gear. And the way we did that is we took 360 degrees divided by the number of teeth, and that gave us the angle between teeth. Similar type of concept here, except instead of 360 degrees, we need to take the circumference and divide it by the number of teeth. So if you consider that pitch diameter circle, if we take that
circumference, yeah, but the okay, what?
Lay it out straight, that would give us our circumference. And if you remember back from your geometry days, there's a formula for your circumference, and that's 2 pi r. But if we write it in terms of diameter, it's simply diameter times pi. So diameter times pi will give us our circumference, and if we multiply that out, it comes out to 150.796. And if we divide that by the number of teeth, which we know is 24, that gives us a spacing of 6.283 between teeth. Now, the cool thing with Fusion 360 is we don't have to type that number in here. We can actually write it in terms of the formula. So you can do the math directly in these dialog boxes. So I'll start with a open parentheses there, and I want to know my circumference, and like I said, that is going to be the diameter times pi. Now I know our diameter is 48, so I'll have times pi. You have to write that with capital P, capital I, close parentheses, and then we're going to take that and divide it by the number of teeth, which is 24 teeth, and there we go. It's got our spacing right there, and I'm going to increase the total number of teeth here, the quantity to 21, and you should get something like that. We'll click OK. And we can measure that spacing, right? So if I go to inspect and go between this tooth here and the same point on the adjacent tooth, I have it right there, 6.283. Awesome. All right, now we are cooking. So let's go ahead and continue the design of the rack. I'm going to create a sketch, and I'll just click on this first tooth here, and I'm going to hit P for project, and I'm going to project that left point and the right point here. Click OK. And then next we'll grab our 3-point rectangle tool here. So the 3-point one is going to be useful here because we can simply click on the first point and then click on the second point here. And then I'm just going to come down. Let me move to the right so we can actually see where it's showing the distance there. I'm going to type in 3 millimeters and hit enter. Okay, E for extrude, we'll select that profile. Same idea here. We're going to reference the back.
All right, I think I got it. Let's see if I can do it. So, okay, there was a lot in there. Okay, so what do we want to do? We want to make a new sketch on here. This is... Okay, so we want to make a new sketch. And we want to... Okay, so this is the part that I don't really know about. But we want to project these guys. Okay. Then we want to hide the body, right? We want to hide the other body. Okay, now we have this, but we need to delete this guy actually. Okay, we need to make a line. Okay, then we want to delete these guys. Oh. Okay, there we go. What the? Why can't I delete this thing? What? It's so random. Okay, there we go. I don't know why that was so weird. Okay, so now we want to create arc, tangent arc. Okay, now we should be able to select this thing, and we want to extrude it. To object. This face. Okay, cool. So now wait, I feel like I missed something.
Project the outline of a single tooth. And now here it's important that this one tooth is facing completely vertical. So I'll hit P for project, and I have specified entities here selected, and I'm just going to click on the outline here. Just be careful, you do have to make sure you get the line. If you accidentally click on these curves here, let's see, you click between these two lines. You know, your is just clicking under the point, be good. This one over here is even. Now you can see if I click on it, away from here is from zooming in to and within my rack component here, I can say I have.
Oh, okay, wait. Oh, wait. Did I do? Okay. Cool. So now we want to do rectangular pattern, bodies, axis, and then what is it? We want spacing, and then we want what is it? 48 times pi over what? 24? What is that? Okay. And then we want 21 of them, I guess. Oh, and we want it symmetric. Okay, cool. Did he get 1,000,000 bodies though?
Two bodies. For a couple important things we're going to speak to. And we did that is we took and I number one here.
Okay, yeah.
Same point and the adjacent to.
All right, nice. So then just create a sketch here. Project this point and this point, and then we do a rectangle, 3-point rectangle. All right, this thing is not so bad. And then we want to extrude this to object. Okay, join. Nice, and now we only have two bodies. All right, sweet. That was not so bad. I can't wait to... Oh, wait, hey, my 3D print is probably done. Ugh, this is so annoying. There's something about that... God, that bothers me so fucking much. Whatever. Okay, so I guess what I'm gonna do is just not use that second one. Anyways, I need to. The fuck? I need to go here. Now where's the? Oh, it didn't save my thing. Is that a joke? I need to offset it more. I just tried to put it on the thing, and the clearance wasn't enough. So what if I just try to do this? 0.1. Oh wait. This thing. 0.1. Okay. Let me select. I select the area in between there. Yeah. So then here, I want to extrude it -15. Just take a little bit more area out of there. Okay. I'm going to save this again. Whatever. Okay. Prepare, delete, add, hat 2. It's so annoying that it puts it over there. I'm hoping it's not. Okay, whatever. So let's slice it, and let's print it. We're going to print it using this. Okay. We're about to find out. I need to get some water. I need some water, bro. Oh, wait, I just got an error. Oh, no, that was from the old error. Just got a new subscriber on YouTube. I'm sick, bro. Okay. All right, so let's finish this rack and pinion. And let's see. Okay, so I haven't really said the plan for this whole thing, but the plan is there's this playlist of 12 different basic mechanisms, and the idea is to make fully 3D printable designs of all these, just so that I can sit around and look at them and play with them. Because I feel like these mechanisms are like the platonic solids of mechanical engineering. They're like, this is how you translate force. I mean, it's engineering, but it's also just like so practical. Oh, I also want bevel gear. Oh yeah, bevel gears is in here. I really like bevel gears. My favorite ones are, I like the universal joint. I like bevel gears. I like the worm and wheel. Oh, and I love the lead screw. I really want to make the lead screw. Okay, I'm gonna get some water. Okay.
Point to 3. Okay. And now we have our rack here. Okay, perfect. So we're all set with the rack, and we have our gear here. If I toggle the top visibility of the parent component.
Dude, how did he make those colors? I really want the colors. Wait, why is this? Oh, wait, I have to. Okay, there we go. But he didn't do appearance. He like. Bah, what the hell? Yeah, that's what I want.
Today we're going to be talking all about colors. First thing I want to talk about is under the Inspect tab. You scroll all the way down to the bottom, we will see Component Color Cycling Toggle.
Oh, baby. That is nice. That is real nice. Okay. Shift N. It's so easy.
We can see them both here. And so next there's one more thing we need to make, which is just a base to, put this whole thing together so that, it can hold it in place and it can spin. So to create the base, we'll first have to create a new component. Right click, new component here. We're gonna call this one base. Click OK, and we'll create a sketch on this mid plane here, so that green-blue plane. If you're having trouble selecting it, just untoggle the visibility of that spur gear and go ahead and click on it. And okay, we're gonna bring that gear back on so we can see it, and we're just gonna move the view cube here so we're looking at this orientation. In my screen, it's gonna be the left view here with the left written downwards. All right, so here we're gonna project a few points here. So P for project. Actually, we'll do a couple lines and a point. So we're gonna do this line here, the bottom, and then we're gonna project just the top point here of our gear. So we're bringing those points into this current sketch. We'll click OK, and now we should see these purple lines and points. We're going to reference those to create an outline here. So L for line, and here I'm not going to worry so much about distance or whether my lines are straight, so I can just kind of do something like this, just being sort of purposely sloppy here just to kind of speed things up. But it doesn't matter because we're going to come back down and close it here, and then we'll add some constraints to make it exactly what we want. So you should have something like this. We basically are just drawing sort of an L shape.
So, but he's in the mid plane. So what he's going to do is he's going to extrude, and then he's going to extrude both directions. Then he's going to deselect the gear and then draw a circle in the midpoint. Or maybe he'll project it, and then he'll just extrude cut this. Or wait, is there already a circle in the middle of the gear? Okay, so he's going to extrude out a cylinder from the projected circle that's there. All right, I feel like I could probably do this. Let's try this. So what do we want? We want to make a new sketch. And yeah, we want this guy. And then yeah, I do want to rotate it like this. And then let's enable this again. And so now we do need to project, and we need to project this. Oh wait, he did the lines actually. Yeah. Okay. All right, so now does his actually go over? No. Well, it does go over it, actually. I just need it here. Okay, so I'm just going to get the rough. Okay, so we're going to extrude this. One side, wait, two sides. Oh, and unique, no, symmetric, yeah. We want symmetric, and we want it to be two objects. Oh, wait, we can't do two objects. It's kind of annoying. That's actually really lame. We can't do two object. Oh, wait. I messed this up. I always forget this. Okay, so we need to go back. Undo all of this. Okay. New component. Base. Okay, now we make a new sketch on this plane. This plane to this way. Re-enable this. Project this. Okay. Wait. Let me do it. Okay.
And now I'll go ahead and grab my horizontal / vertical constraint, and I'm just going to click it on each one of these lines to make sure they're either vertical or horizontal. Now I'll just click on all of them. If they're already vertical, for example, it'll just give you an error, but that's fine. Okay, next we're going to add some dimensions. So D for dimensions, I'm going to click on this top edge here, and I'm going to make that 5 millimeters. And now I'm going to keep adding dimensions, and I'm going to continue to reference that dimension, the first one, by clicking on it. And you see here, it'll say D55.
Okay.
Yours will probably have a different number, but as long as it's saying D and
I'll make
referencing
mine
the first
4.
dimension, you're good. And the reason I'm doing this is because if I want to come back and change that thickness here, all I have to do is change that first one. So let's say I wanted to do 7, you'll see that they'll all update and I don't have to worry about changing each one of them. Okay, one more dimension, just this line here. I'm gonna make this 65. And there we have it. I'm gonna click Finish Sketch, click on this profile here.
Okay. Okay. Then and then what was the other one that he did? From here to here. And then and then this. Okay.
Extrude, and here I'm gonna go with a symmetric extrusion, and I'm just gonna pull this out until it extends past the rack here. So let's say we'll enter a distance here, 70 looks good. All right, okay, and there we have it. I can untoggle that sketch in there, I don't need to see it.
Okay, cool. Finish sketch, extrude, symmetric. A low taper fade. Okay. Dude, Eric Doe is actually crazy. That's what I wish I was doing in college, bro. Alright, so that's good. So now if we go here, that looks pretty good.
And there is our base. So if we activate the parent component here, the whole assembly, we should have something like this. Okay, almost there. Just a few more things we need to do. I'm going to go back into that base component, and I want to go ahead and create.
Has it been 12 minutes? Oh, see, and then I didn't get the error. So there's just something lame about that freaking second slot that just, whatever. I ain't let it stress me, bruh. I ain't let it stress me none. Okay.
Create the sort of pin here to come out for the spur gear to be able to rotate about. So let's go ahead and create that. And so we're in the base component here, and I'm going to create a sketch on the back here. And I'm going to orbit back to the front, and I'm going to project this circle here. So P for project. I'm just going to grab it, click OK, and if I go to the back, I should see it. All right, we'll go ahead and untoggle bodies there just so we can see the circle a little better. And I'm going to untoggle rack and spur gear components. And for sketches, I just need to see the second sketch here, not both of them. All right, here we're going to come in and do an offset. And I'm going to click on the circle here, and I'm going to do a 5mm offset. And then finish sketch. Okay, I'm going to bring that sketch back into view, and let's also look at the body there, because we're going to select these two circles and extrude them in. So E for extrude, click both of these circles, and I'm going to go inwards a distance of -3mm. Operation is going to be new body, and then I'll click OK. And if I untoggle the top body here, I should see that I should just have this disc here. I'm going to click on that second circle, E for extrude.
I don't know why he did that.
This time I'm going to bring in body 1, and I also want to see that spur gear, because what I want to do is extrude this out and have it go past the gear. And here, -20mm looks good. Now, I want to have this be a join, but I don't want it to join the back portion here of that base. So let's untoggle body 1, and I should just have this here. In fact, it's not going to go ahead and join into the spur gear because that component is not activated. So I don't need to untoggle the visibility of it, but we don't really need to see it anymore. I just wanted to reference it. Now we can just go ahead and untoggle it, and we should have something like this. I'm going to click OK. And there we have it. That's our pin. Let's bring back body 1 of the base component here, and we'll untoggle sketches.
Is that because he wants to print it separately?
Between this and this body,
what is the purpose of having two bodies?
Overlap each other. Now I want to use the pin here to cut out an opening for it on the base. So to do that, we're going to go to Modify, Combine, and our target body is going to be the base here. The tool body is the pin. Operation is cut, and we want to make sure Keep Tools is checked because we want to keep our pin. Click OK. And now if I untoggle the pin there, you should see we have the hole there. And the idea is to be able to just kind of snap the pin in there. Everything looks pretty good here. One final thing we'll need to do is factor in how everything is going to fit together. And so we're going to have to design a little bit of clearance fit here. And so to do that, consider our rack sliding back and forth here. We're going to need to give it a little spacing, otherwise it's just going to bind or probably won't even fit. So let's start with that. I'm going to go ahead and grab my offset face tool here under the modify menu. I'm going to click this surface here on the back and on the front. So two opposite surface, and I'm going to go a distance of -0.2 millimeters. Now this is something you may need to experiment with or just know your printer. I'm going to go with 0.2 because I think it'll be good enough for my printer. You may have to do a 0.3 millimeter clearance there if you find that you still need a little more room there. But I'm going to go with 0.2, click OK. And the next clearance I'm going to want to put in here is on the opening here for our pin to fit in here. And again, we'll go to Modify, Offset Face. I'm going to select these two surfaces here. And I want this one to be more of a friction fit, so I'm going to do -0.1 and click OK or Enter. And there we have it. Now, if I bring that body into view, I can see if I go here and zoom in, there should be a little gap in between there, which is exactly what I want. So let's go ahead and activate the top level of the component and bring all components into view. And there we have it here. So if I zoom in here, I can see a little spacing between the front and the back, and of course the spacing between the pin there. Okay, so that's how we create this rack and pinion assembly with the spur gear, our rack.
Pretty sweet. Okay, so let me finish it, and then I'll do the okay, so what did he do? He's drawing a sketch on here, but then he's projecting this thing, and then he offset it by 5 or something. And then so let's go back to that. Then he extrude with a cut. And I'll do -2 because my width is not that much. So, okay. Then is that the right sketch? That's not the right sketch. Wait, which no. Hold on, I fucked this up. Okay. Okay, so we want a new sketch on here. And then we want to project this guy. Okay. Then we want to offset this by 5.
Inward. Go ahead and click OK. And if I go to the... So let's go ahead and create that component. And I want to go ahead and create components here. The whole assembly, we should have something like this. Okay, almost there. There's a few more things we need to do. I'm going to go back into that base component, and I want to go ahead and create the sort of pin here to come out for the spur gear to be able to rotate it out. So let's go ahead and create that. And so we're in the base component here, and I'm going to create a sketch on the back here. And I'm going to orbit back to the front, and I'm going to project this circle here. So P for project, I'm just going to grab it, click OK, and if I go to the back, I should see it. All right, go ahead and untoggle bodies there just so we can see the circle a little better. And I'm going to untoggle rack and spur gear components. And for sketches, I just need to see the second sketch here, not both of them. All right, here we're going to come in and do an offset. And I'm going to click on the circle here. I'm going to do a 5 millimeter offset, and then finish sketch. Okay, I'm going to bring that sketch back into view, and let's also look at the body there, because we're going to select these 2 circles and extrude them in. So E for extrude, click both of these circles, and I'm going to go inwards a distance of -3 millimeters. Operation is going to be new body, and then I'll click OK. And if I untoggle the top of body here, I should see that I should just have this disc here. I'm going to click on that second circle, E for extrude again. This time I'm going to bring in body 1, and I also want to see that spur gear, because what I want to do is extrude this. This up in that second circle, E for extrude again. And this time I'm going to bring in body 1, and I also want to see that spur gear, because what I want to do is extrude this out and have it go past the gear. And here -20 millimeters looks good. Now I want to have this be a join, but I don't want it to join the back portion here of that base. So let's untoggle body 1, and I should just have this here. In fact, it's not going to go ahead and join into the spur gear because that component is not activated. So I don't need to untoggle the visibility of it, but we don't really need to see it anymore. I just wanted to reference it. Now we can just go ahead and untoggle it, and we should have something like this. I'm going to click OK. And then
he wants it to be a join, but then you undo. Oh, wait. Oh, no, he extruded it not as a cut. He did this.
Also
yeah,
okay.
okay. So let's undo. What the hell? Okay, and then I just happen to know it's -20. And then it's going to be a join. And then I didn't really know that this is how this works. But so now if I do OK. Okay. So that's pretty cool. And then I feel like, oh yeah, he does offset face these. But how does he, so I can save this individual body as a mesh. Okay, so then I'll have 4 prints.
at the body there because we're going to select these two in operation toggle insert, and I also asked to have and I should just have this here. In fact, it's not going to go ahead and join into the script button, and we should, let's sketch this body. We've got two bodies there and they overlap each other. So to do that, we're going to go to modify here to cut out an opening for it on the base. So to do that, we're going to go to modify, combine.
Okay. Oh wait, did I select it the other way? I forget how this works.
Our target body is going
Yeah,
to
the target body
there.
is the whole thing. So let's cancel that. Combine, target body.
Here, the tool body is the pin. Operation is cut, and we want to make sure keep tools is checked because we want to keep our pin. Click OK. And now if I untoggle the pin there, you should see we have the hole there. And the idea is to be able to just kind of...
Okay. Nice. So it'll just slot in there. Okay, so then what he does is he disables this and he clicks on this and this and he does Q and it is minus 0.2. Oh wait. Okay, so now if I inspect the distance from here to here, 13.1. I don't know if that's accurate. Let me undo it. Oh yeah. Okay. Wait. So here, it was 12.7, but then, yeah, okay. 13.1. So that should be good.
Snap the pin in there. Everything looks pretty good here. One final thing we'll need to do is factor in how everything is going to fit together, and so we're going to have to design a little bit of clearance fit here. And so to do that, consider our rack sliding back and forth here. We're going to need to give it a little spacing, otherwise it's just going to bind or probably won't even fit. So let's start with that. I'm going to go ahead and grab my offset face tool here under the modify menu.
What the?
I'm gonna click this surface here on the back and on the front. So two opposite surface, and I'm gonna go a distance of negative 0.2 millimeters. Now this is something you may need to expand enough for we'll need a little more. We're gonna put in here is on the offset face. I'm gonna select these two surfaces in here, and again we'll go to
okay, wait, so let's just, instead of this, let's just do this, and maybe it changes the selection criteria. It doesn't, though. Yeah, that's so fucking annoying. Okay. Okay, so we did that one. Now, how are we going to get this face? I don't even get it. Okay, there we go. And this is going to be minus 0.1 as well. Okay.
Modify offset face. I'm going to select these two surfaces here, and I want this one to be more of a friction fit, so I'm going to do negative 0.1 and click OK or enter, and there we have it. Now if I bring that body into view, I can see if I go here and zoom in.
All right, so I'm gonna export all of these guys and send off the print. Well, I need to go get the new hat. I'll get the new hat and then I'll send all of this off for printing, and then I can add the motion stuff because I've never done the motion thing. Okay, so okay. Just make a folder. I don't know why it keeps exiting out of there. Wait, where is it? Oh. Okay, so now this will be the first time that I where's the gear? Weird. Or wait, this is called the pinion. Okay, so yeah, so this is, I don't know. I can clear out supports from there. If I don't know. Okay, this needs this thing. This is fine as it is, and then we just need pinion. And this goes here. Okay, now for the color picker, I want the moving stuff to be. Okay, this is 2. This is 2. This is going to be 1. And this is going to be 1. Is it going to say I need well, maybe we'll find out. It's going to take an hour. It's kind of annoying, man. Can we... Whatever. That's fine. I selected the colors, though. Alright, I guess we'll see, but why is it only saying this? Right, see, but I selected the...
Matthew here from the Mini Wargaming Forge, and today I want to show you an unboxing.
This is literally a retarded video. Printing in multiple colors literally doesn't go into Studio at all.
So that's what that looks like. You change it to whatever you like, and then you can press on the color and change the color. So leave the black the way it is. We'll make this one pink for contrast. This one can be orange, and we'll do gray over here. So there's our colors that we're going to be using for this project. Now you just bring in whatever part, STL file that you want to use. So I'm going to use a calibration cube here. So it gets imported entirely as your first color. And then from here, you go into the paint tool. And so right now we're painting with black. Tool type is a circle. You get your pen size and section view. So let's change it to pink. And
Wait.
so right now we're just using a circle.
Let's go back to prepare. Oh, but I have to paint it? No, I want the whole thing. That's kind of stupid. Okay, I'm guessing that that is good. What is this thing? What is this? It's weird. Is it more efficient to just do two? Oh, there we go. Okay, but yeah, but in actuality, I want this. Or wait, no, I want it the other way around. But this, okay, so wait, I need to undo. Okay. All right, so I don't know what the hell that is. Okay, so this thing moves, so I want it to be white. But then this thing... Oh wait, we need to actually... Yeah, so body one is black. This will be my first multi... I think it's going to add a lot of time to the... Yeah, see, that doubles the amount of time. Maybe it like doesn't have awareness of its own geometry where it can like, I don't know. Let me new project. Oh, L. Okay, wait, let's just do these two. And these are going to be black. So we select both of these. Okay. So I guess it needs that calibration cube for the colors or some weird thing. But so if we slice this plate, let's see what it says. 48 minutes. Is this going to be annoying to get off of here? That's the question. I think it'll be all right. Okay, so let's print this. Oh yeah, and I forgot to say the hat. Do I have it? I think I might have left it up there. The hat that goes on the servo, it fits, but now it's like way too loose. The backlash is like really high. But yeah, so the next thing, I guess, is to take this and instead of that, build a little mount that allows me... Yeah, so we're going to have to change this pretty significantly. All right, well, let me print this because then by the end of the stream, we'll... Okay, even though we followed a guide, now we can do the motion.
There should be a little gap in between there, which is exactly what I want. So let's go ahead and activate the top level of the component and bring all components into view. And there we have it here. So if I zoom in here, I can see a little spacing between the front and the back, and of course the spacing between the pin there. Okay, so that's how we create this rack and pinion assembly with the spur gear, our rack, and we have our base. I'm gonna end it right here. In the next video, I'll show you how we can add motion to our components by applying joints and also a motion link. So stay tuned for that video. All right, if you have any questions or comments, leave them below. Also check out the links below to my Fusion 360 resources. I've got courses, a weekly live class that I offer, or if you simply want to support me creating more content like this, consider visiting my Patreon page and supporting my channel. All right, guys, I will see you in a few.
Or wait, why did I do that?
Hey guys, Vladimir here with Desktop.
Vladimir here.
Welcome to our third and final installment here in this series of modeling a rack and pinion assembly. So in the last two videos, I showed how we created all the parts you see here, the three different components, creating a spur gear, and then using that to create a rack here. So in this final lesson, I'm going to show you how you can add joints and motion links here to be able to allow the turning of the spur gear to go ahead and move the rack back and forth and put that relationship together. So right now, as you can see, I have them as components so I can freely move these. And when you do that, make sure to always come back here and click on the revert position to bring everything back. Otherwise, if you click on capture position, it's gonna go ahead and move that location. All right, before we jump in though, there was one question I received that I wanted to address, and that was from, I'm going to say, yeah, Usafa, 1987. Good stuff. I'm enjoying this series. One critique, it wasn't obvious why you were making the pin as a separate body. I assume it is to be able to 3D print the base without supports. But if you mentioned this reason, I didn't hear it. Okay, that's actually a great point. I completely forgot to mention why I was doing that. What Usafa is referring to is if I untoggle the rack here and the spur gear, you can see in my base component, I have that as two separate bodies, the pin and the rest of the base here. He is exactly correct. It was in order to be able to 3D print this, and I'll show you what I mean here. Let's jump into Prusa Slicer. If I send this to 3D print as one piece, this is how, well, I've got a few options on how I can lay it out, right? Like if I print it like this, then I have to go ahead and enable supports to be able to support the pin here, which I want to avoid, right? So let's say if I turn it on its back like this, then I don't need supports for the pin, but I will need supports on the bottom here. You know, maybe I've got another option here where I can lay it on the sides like this, but then I need supports for the pin here. So I did try this out, and as far as my options were, I figured my best orientation would be like this and not do supports for the pin, but have it for this sort of overhang here. And it worked okay, but the problem is that, you know, I would then have to clean up supports. So let me just show how that looks here. Supports everywhere, and then if I slice that. So this right here, all the supports needed to be cleaned up, and I was able to pull it out and clean it up. But the problem is you didn't get a rough finish over there. Then, you know, you do have to do some additional work to try to sand that.
Yeah, that's the part where you really don't want to.
It's just extra work, and if you don't get it perfectly
so
right,
what did he do?
then the rack just doesn't move smooth.
So he
back
printed
and
it
forth,
vertical,
you know,
all
as
tall
it
like that?
Travels across it, and it just, you know, you create
Should I cancel
extra
my
friction
print?
there. So I wanted to avoid that as well. So what I decided to do was then to just go ahead and separate the two and print them in separate pieces. So if I click on the model here, I'm going to go ahead and split to objects. And here you can see we have the two different parts here. So now the pin can print perfectly fine like this without supports. And what I can do with the rack is I can turn it. And here, let's see, I can either, you know, flip it in this direction, and that would print fine without supports, or I can also flip it in this direction here and print that fine without supports. So that's the reason.
Oh, bro, am I
Why I did
dumb as fuck? What did I do? All right, hold on. Nice. It didn't actually start printing yet. Okay, cool. So let's go back here. You don't need supports for this circle? I guess not. That's pretty sweet, actually. So then, prepare. Okay. Okay.
Decide to go ahead and split these out. If I can design my way out of supports, I will normally do that.
Yeah.
That's usually my first option, is just to try to either separate the design into different parts or add, sometimes it only takes like a fillet or a chamfer to be able to get it to.
I love the
So,
like
yeah, if you can
mechanical
design your way out of using
design,
supports,
no free lunch theorem type.
I would definitely recommend that, and that's what I did here. All right, let's go back to Fusion now, and we'll continue with this design here. So what we're going to do is add some joints. And since I modeled everything in place, I can go ahead and take advantage of my as-built joint. So here, you'll notice you've got a joint option, and then you've got an as-built joint option. Now, the nice thing about as-built joints, if you design your components in place, you can just go with as-built joints, and it makes the process a little bit more simple. So I'll simply click on as-built joint. Oh, one thing you have to do before, and I always kind of forget this and have to go back and do it, you have to ground one of your components before you start adding joints, because you have to tell Fusion which one is not moving. And so we're going to ground the base here, because that's the part that's going to be staying still. So I'm going to go here to my components. I'm going to grab the base, right click and go ground. You'll see a little red pin there. Okay, so now I can't move the base. Now I go back to assemble, as-built joint. Then I'm going to choose my two components. I'm going to choose my spur gear, and I want that joint around this pin here of the base. So it doesn't matter where I click as long as I click on that component. And I'm going to change my motion here to revolute, because that's the kind of joint that I want. And the third thing I need to do is to tell it the axis of rotation. So here I'm going to go, and if you click, you'll see I can select either the circle or the center point, and it puts that little flag right in the center. If you just like over your mouse, it says select the snap point to define the joint origin. I'll click there, and now you can see that the spur gear starts spinning around that pin. You can click here to preview motion, and I'll click OK. That looks good. All right, next we're going to go back and add a slider joint to the rack here. So assemble, as-built joint. Again, same thing. I'm going to select my two components. I'm going to choose my rack and then choose the base. And I'm going to go to motion and change it to slider. Now, with the slider, what you have to do then is tell it the where you want it to slide, or give it the edge you want it to slide about. So here, if I kind of hover over an edge, you'll see it'll show. I'm going to snap to that middle point. And if, again, I let go of the mouse, it says select a snap point to define the joint origin. So I'm going to click right on that edge, right on that point, where the arrow kind of shows the direction. And now I've got that motion. So there we have it. We have the rotational and the translation here, the slider. Perfect. But one thing we can see here is we are defining some laws of physics. So let's go ahead and fix it so that they interact with each other. And to do that, we're going to go back to assemble, and we're going to select motion link. Now, the motion link, so if you just kind of read there, it says defines a rotational and translational relationship between joint degrees of freedom. Select the joints and specify the values. Okay. The important thing to remember with motion link is you set it between joints and not between components. If you try to click on components, nothing happens. You have to go to your browser here and tell it which joints do you want to set the relationship with. So here we want a relationship between the revolute, the spur gear here, and the slider, the rack. And you can see it happening there. I'm going to delete that for a second because I remembered my last value there. But usually you see something like this. It's just kind of spinning like crazy. It's kind of hard to see what's happening because it's going so fast. But if you look at this dialog box, you see you have your two different joints, your revolute and your slider. And it's asking you for every 360 degrees here of your revolute, what is the distance that you want your slider to travel? And you can change this.
It's so funny how like unaware it is of what it's modeling, because it has to be generic, but it's like, damn, figure it out for me.
It's math easier. So for every 360 of this spur gear, how far do I want it to travel? Well, if you remember from our last lesson, the last video I did, we kind of figured that out. And that
needs
really
to be
becomes the circumference
48 pi.
circle. You can go back and see the math in my last video, but here we just have to type the formula for circumference. It's going to be the diameter times pi. Now we determined that our diameter was 48 millimeters. So we just type that in times pi, which we can just write as capital P, capital I, and then just click OK. Now we can see that these perfectly match up. And you can tell if you kind of just zoom in here, how if you go to the last gear, that's perfectly lined up. And then you kind of go to the other side, you can see that you're still perfectly lined up. If there was any error there, this.
All right, so let's do it, and then we can move on to the second one. Okay. So Shift J. Oh wait, we need to ground this thing. Base, ground, pin, ground. I guess got changed. Pins base to unsaved. All right, I'll do this. Shift J. Oh, wait, hold on. Let's undo. Select this. Let's undo. Is this still pinned? If I do this. Okay. pin versus ground. I think it's going to be ground. Anyways, now we want Shift J, this thing, and what? The components you selected are rigidly joined. Okay, what if I try to change this from to pin? Because that seems like what it is. Bro, what? At least they make this selectable. I feel like I have so many error messages, even bamboo. It's like you can't even select it. Okay, maybe you just don't need to do that anymore. Okay, so if I unpin, wait, is this? Oh, somehow that got. That's interesting. Wait, did I just ruin everything? So wait, but this we do want to ground to parent, and now we want to, oh, cancel, Shift J, type revolute. Oh, no. Cool. Okay, then we need to do, and then we can just click this flag. Oh, what? How come I can't manipulate this fucking thing? All right, then we Shift J again, and we select this bad boy, and we make it slider. And we want it to slide in the x-axis. Okay, cool. Okay, did he set any of these limits? We don't need to look at this. Just say okay, and then now joints. Now, what do we want? We want motion link. And then we want, for this, we want the distance to be I think it is. I think it is correct. So wait, how do you actually manipulate them? Wait, animate joint. But how did he?
Would start to travel and your gears would start to interfere. So perfect. One thing I do want to show you, let's go back to that motion link here in edit feature. If you ever have it going the
Times 1 millimeter. Did I fuck that up or something?
fast, but if you look at this dialog box, you see you use the circumference of that pitch diameter circle. You can go back and see the math in my last video, but here we just have to type the formula for circumference. It's going to be the diameter times pi. Now we determined that our diameter was 48 millimeters, so we just type that in times pi, which we can just write.
It's kind of funny that there's just literally no physics engine in this thing at all.
Capital P, capital I, and then just click OK. And now we can see.
Oh, what? Bro, I wanna fucking. What? How come I can't move this thing?
That these perfectly match up. And you can tell if you kind of just zoom in here, you know how if you go to the last gear that's perfectly lined up. You know,
Oh, there we
and you
go.
kind of go to the other side, you can see that you're still perfectly
See, mine's
lined
like
up.
not on the front.
You know, if
It's
there
like
was
on
any
the
error
back of
there,
it.
this would start to travel and your gears would start to interfere. So
That's pretty nice.
One thing I do want to show you, let's go back to that motion link here in Edit Feature. If you ever have it going the opposite way, like, let me just click that reverse button, where you turn your spur gear one direction and the gear goes the opposite direction. You see here, it's not going in the correct direction. You just click that reverse button. Let's go back here, Edit Feature. Just you either check or uncheck the reverse, and that'll fix that.
Dude, that's so cool. He just can click and drag the whole thing. Oh, wait, I can too. Okay. Nice. All right. What the flick? Well, we can just put it in here. Oh, I'm so excited for this thing to print. Wait, I just gotta... Dude, why do I always get these faulty... Yeah, I feel like the notifications for the app are just kind of delayed. All right. So... That's pretty sweet. Should I just move on to the next one, or should I make a mount so that... It would be pretty cool to... You know what? We should do that. So back in this thing, if I go to this, okay. So what I want to do is I want to make a as-built joint, I guess, to the hat. So Shift J. I guess I don't have a... Why don't I have as-built joint? So it's this thing. Component 2. What's this whole thing? But I guess it's this. Snap, it's going to be... So wait. Oh, this is all one body? Okay. I'm going to try this thing all over again. So here I want to do new component, call it stepper. And then in there I want to insert not a mesh, insert component. But then I can only, dude, this cloud bullshit is like actually ridiculous. Insert derive. Okay, wait. Because I don't want it to be the... No, not in electronics, bro. Is that really? That's what they want me to do? So, in here I have this. Assets. Okay. So once that upload is done, I guess. What? Dude, when is it gonna... Okay, whatever. I'm gonna update it and take like a little break to wait for it to upload or something. Let's see, how long has this been going on? 2 hours? Ah, it took 2 hours to do this? Jesus. Are you looking up? Are you asking why? Do you wanna come, baby, go hide? I could shift shapes, but I can't deny. We could put it all to rest just for one night. Dude, why is it 9 minutes? I just want the song. Dude, please don't copyright me. I'm just trying to share my love of music. Sunday morning, been in the blinds. Oh, there it is. Million ways to kill the time. And I never really know what you're thinking about. And I know I'll never really figure it out. All experience ever does is confirm my doubts. Convinced that I don't really feel it. But it's funny how you know, it's just anyone to know. Like it's gone out there somewhere I don't know. Ever misses the snow and all these thoughts I can't push out of my mind like 100 twisted ways I might die. It's kinda slow. These are things I don't need anyone to know. Oh. Okay, so let's fucking lock in. Action was kinda slow. These are things I don't need anyone to know. That's actually crazy. This thing is... I mean, they spent the time to color the wires. That's pretty nuts. No, it doesn't matter. 'Cause I never really know what you're thinking about. Okay, let's fucking lock in, bro. What the hell? What? Mm. So I extruded it, I offset it by 2.15. So I do -2. That should be pretty good. So now we need to take this face, and I bet we need to... Yes, now we extrude this by 5... Oh, no, we extrude this by probably 13. No. 15. Okay. Okay, so now as built joint. Oh wait. No, but this. What? Dude, it's not though. It's not even ground to. As built joint is so much better. I don't know what this is. Why don't I just delete this? But you know what I want to do? Okay, so I want to do this, but then I want to go back to this extrude and make it 13 again. And then I want to... How do I move this thing? I don't get how to move these, bro. How do I play it? Play the motion. Yeah, so but this piece doesn't move. Also, why is it so wobbly? The hell is up with that? So, okay. So we actually need to... Dude, what? Some stuff about this program is so fucking annoying. Okay. I wish there was just a play button. Okay. So this thing is actually... What does that even mean? I literally have no idea what that means. Axis through cylinder cone torus. Okay. See, but I can only select a full component. But if I could select a feature... There's only one body, but there is a way to... I wish I could, like... extract it. Assembly context? What is that? Let's look it up.
Sub-assemblies. Now, if you want parts inside of a single file, to do is create a joint for this new instruction. So the first thing we're going to do is activate the component here. And the way that I've done this, I already like the position that this is here. This also goes here. And the joint right here is going to Revolute. And Fusion wants us to put an origin for this Revolute somewhere, so let's put that in the middle here. And that is looking pretty good to me. So click OK on that. And now we have this lead screw jointed to the rest of our model. The next parts that I want to add to this design are the shaft collars that are going to hold this lead screw in place. Now to keep the file organized, I want these to be subcomponents of the lead screw. So I'm going to activate the lead screw component first and then insert a McMaster-Carr component again. Then we are going to look for a shaft collar. And then we want a metric one, of course, and I want a one-piece design.
Jointing motor bracket, that's probably what I want.
And again, for that, we're going to create a quick little helper sketch. So I'm going to create a sketch on here and create a construction line. So let's project first. And then create a line from the center here to the center there. And we can hit E for extrude. And then here we have a little bit of an issue that we have because we started the sketch on this thing over here. So let's see what we want to do here.
Dude.
Actually, we just want to extrude all of it. So we want to extrude this. And next, how thick do we want this plate to be? Well, I think 10 millimeters will do. That looks about right to me.
Dude,
so
people
click
that are
OK.
beasts at this stuff
Let's
are
continue.
crazy.
The next thing I want to do is create the holes for the push rods to come through. So I'm going to create a sketch on this surface over here and then make a circle in the middle, and let's give that a diameter of 30 millimeters. And I'm again going to isolate this component here so that I can see what I'm doing. This can be construction geometry. And then I will draw a construction line a sketch on
Where's the
here.
part where the actual motor
turns?
turns?
Component and press compute. And then what you get here is that we have 4 push rods that are interfering with the bottom plate over here. And we also have the volume here that they're interfering in highlighted. And we also used this tool before, for example, to check the meshes in the gear tutorials that I've done. So this is a handy tool to have, but let's move on with modeling. At this point, our pusher plate subassembly is still able to float around like this, so of course we now want to joint it. And for that, I'm going to use an as-built joint, and it's going to be a joint between this thrust plate here, and I'll take this vertical rod over here, and let's put the origin of that joint over there, and then we can click OK. And now we can drag this thing up and down, but it can no longer float around otherwise. But one problem that we do still have is that it can just float straight through this thing here and also at the bottom here, so that's up next to fix. I first want to fix that interference that we had here at the bottom plate, so I'm going to activate this bottom plate component and create a new sketch on the bottom surface of that plate, and then hit P for project these push rods into my sketch, click OK. And then I'm going to create some
Dude,
circles
what a
concentric with those push
fucking
rods,
piece.
and then I'm going to make those all equal sized, and that size is going to be 6 millimeters. And that will either give us enough clearance so that we don't have any rubbing, or we can put a bushing in there because the outer diameter of a bushing will be 6 millimeters in that case. So we can just extrude this up to this top surface over here, and then we just have to ensure under objects to cut that we do not cut the push rod and click OK. And then we should no longer have any interferences. So inspect
Wait, what was that?
we just have to ensure under
Oh, objects. Oh, I didn't. Yeah, I've never used that before.
objects to cut that we do not cut the push rod and click OK. And then we should no longer have any interferences. So inspect interference on the root component, compute, no interference is detected. So now let's turn our attention back to that slider joint over here. And the first way that we can fix this slider joint going through other components is by enabling contact sets. So under assemble, I will enable contact sets and then ensure that all bodies contact is enabled. And now I can push this thing up and down, but as it hits either the bottom or the enable components is by enabling contact sets. So under assemble, I will enable contact sets and then ensure that all bodies contact is enabled. And now I can push this thing up and down, but as it hits either the bottom or the top, it will basically stop.
That's pretty cool.
However, this isn't completely perfect because if I basically apply enough speed, I guess I can just phase through this wall over here. So contact sets can work okay, but they don't work that great.
Dude, there's some like cringe things to design. Like that is
also,
hilarious.
Interference here first, because if you have an interference like that, a contact set will basically bind up your model entirely. And finally, contact sets can also be quite difficult to compute. So with all of that, they are not a great solution, but sometimes they are the solution that you want. So for this model, I'm going to disable the contact set. I don't really find that as a great solution here. And I will go to the slider joint and set that to 0. And then I'm going to add some limits to this joint. So the joint limits here are going to be a minimum of 0, and then the maximum is going to be probably something like 150. So we can animate that. It's going to be actually the reverse in this case, so minus 150 to 0. And then we see that we don't get all the way to the bottom here. So we can actually cancel this for a minute and figure out how far this needs to go. So we can just drag that down here. And then we can read here that this is actually minus 150, so that was almost correct. So let's now actually set those limits. And the limits here, again, are going to be a minimum and a maximum, with a minimum of minus 150 and a maximum of 0. And then if we animate this,
Dude, this guy's
we see that we get basically the right
locked
idea.
in.
And once we
Holy
click OK on that,
cow.
and we just drag this up and down, we see now that we have actual limits that we can't pass through by just applying enough speed. That doesn't work. And also now the push rods are again coming along. Again, in the animations, this doesn't always happen. Usually it doesn't. But once you click OK, everything will snap into place as expected. The next thing I want to do is ensure that the rotation of the lead screw is tied to the sliding of this pusher plate here. So for that, I'm going to create a motion link. I'm going to continue here. I don't need to capture this position. And the joints that I want to link are this
So he
rotating joint
still
here and this
doesn't
slider joint
have
here.
the
And what I want to do here is
actual
ensure that if we have a 360-degree rotation, then this thing has to slide 8
interface
millimeters.
between
So click OK on this.
the
And then the next thing
the
that we have
lead
to check is
screw
ensure that
and
we go
the
in the right
servo
direction,
head.
that we have the right direction on the slider and the rotation. So right now it appears to be reversed because as I'm turning the lead screw, I actually see the threads moving upwards from this perspective, and at the same time the lead screw or the pusher plate is actually moving downwards. So let's go back into now the lead point is with the motor component. And that component is at the shaft coupler that are going to couple the motor shaft to the lead screw. And for that, I'm again going to insert a McMaster-Carr component. And that component,
Dude, that
of
is
course,
so
is going
fucking
to be
cool.
a shaft coupler.
Shaft coupler.
And then it's going to be for round shaft metric clamp on. And then this is a model that I do like. I don't intend to buy exactly this one, but it looks a lot like the one that I do want
Look
to
at
buy.
these prices.
So let's go for product detail.
That thing is
Going to the 3D
$70.
step again, download.
That is insane. Dude, I bet you can
And let's
design
put
some
that
crazy
off to the side for
expensive
now.
stuff in this.
And then what we're going to do is create a joint between this guy over here and the center of this shaft over there. And then we're just going to move that up by, let's say, 10 millimeters. Click OK. And now we want to see whether that actually fits any good. So what we're going to do now is go into the origin here. And then we are going to do a section analysis on this vertical plane over here. Click OK. And now we can see that the coupler is actually a little bit too far above here. So we're going to go back into this joint over here and move that down just a little bit like so. Click OK.
That's
You
it?
could maybe have a little bit of less
It's kind of
space.
interesting because I would think you want to get it as far. Oh, but was it too? Well, yeah, for this one.
So, click OK. You could maybe have a little bit of less space between
What's up with
the
that
motor
gap
shaft
there, though?
and
I
the
don't
lead
really.
screw.
Oh, you know what?
But
That
whatever,
actually
that's
does
fine.
make sense because that's where the
Now
flat
we
part
can
is.
hide the analysis here, and the next thing we are going to do is an as-built joint between the lead screw and this coupler here. That's going to be a rigid joint. Click OK. And now we should see that when we animate the model on this guy, that the motor shaft is forced to turn along with it. And we can also do that from the other perspective here. So if we animate the model here, we see that
Dude,
it
and
works
that
like
thing
that.
rises? That is so cool. Oh. Okay. But how do I get this thing to turn on its own? I don't know if I can. Is there a way to make a... Okay, so... So you can... Okay, it's a separate... Okay. Modify split body... Oh, okay, cool. Modify split body... Invert position. Okay, so... Bodies to split... It's going to be this body. Why can't I select it? Oh, wait. Is it because I have this? What? I don't know why I can't select this thing. Is it... sometimes right click just does not work on these fucking things. Dude, Fusion drives me fucking up the wall, bro. Okay. And I never really know what she's talking about. And I Okay, so break link, what does that mean? Unground from parent. Okay, yeah, we should probably do that. Okay, now, okay, wait, I don't want to hide this thing. I want to select. Okay, so that is the whole thing. Dude. I don't know why I can't select this thing. Bro, I'm hot and bothered by this thing. I don't know how this thing keeps moving. But I just can't click anything.
I'm going to show you how to split a body. There are many reasons you may need to do this. Sometimes you make a form and you really want it to be two pieces, or maybe you needed it to be different components, or maybe there's a cap that you want to have a lid on. There are multiple different reasons that you want to split a body. To do this, let's go ahead and make a body. First, we'll create just a simple box. We'll click on the ground plane, click on the origin, we'll pull out 50, tab 50, press enter, and then go up 50. So this is just a box, and it's just a body, not even a component. So let's split this body. First, if you go to the modify split body, it says we need a body to split and we need splitting tools. Well, we could select this body, but then the splitting tools, we don't have any splitting tools. You see, if I click this face, it just wants to split it here, but I don't have anything. So let's make a splitting tool. You can use another body as a splitting tool. So let's do that. Let's create another box. We'll create it on the ground plane, and we'll just draw it here any size we want, as long as it intersects. We'll press OK. Now let's click Modify Split Body. The body to split will still be this one. Now, when we click on splitting tools, if I click this tool, notice it's going to split it like a razor straight down the middle. If I click this splitting tool, it's going to split the body there. So we have lots of different options. And if I press OK, now you can see I have two bodies.
Okay. I wonder if it has to be separate. Wait. Yeah, what? Dude, I don't know. What the fuck is going on? Ay. Okay, wait. Let me just try this totally naively from a scratch. So we're going to make a circle. Yeah, 30 cents, fine. Then we're going to make a line. Is it? Okay. Are they coincident? And I never really know what you're thinking about. Okay. So we're just going to take this and we're going to offset it. Yeah, by 2. Then we're going to extrude this by 2. Then we're going to go under here and we're going to just take this. Oh wait, I probably did new body. Or I mean, I probably didn't do new body. Oops. Okay. Oh. We have 2 bodies. Wait, hold on. I want to draw on this face. And then I want to project this. Then I want to hide this. Then I just want to extrude this. Okay. Now, Okay. Cool. Wow. And I never really know what you're thinking about. Play it again. Wait, but this thing needs to rotate too. Okay, so let's just draw. Oh, wait. Hmm. Fuck. Oh, you know what it is? I get it. Okay, so assembled, cancel. Assemble as built joint. Select this and this. Hmm. Okay. And this is going to be Revolute. And if we disable this guy. Okay. Now. Okay. Um. Where's the play button? Can I just get this thing to play? All right, and then motion link. But they move at different rates. First off, I don't even get how that's possible. Yeah. I mean, they literally are saying they're moving at the same rate. Dude, this right-clicking thing is driving me up a wall. Why can't I right-click them? If I do that, I can't select anything? This feels like a bug. Fuck. Okay, well, I don't know then. I don't know how to do this. Oh, sick. Okay. Okay, so this is the piece. It doesn't really comes out kind of too easily, so I'll put some glue in there or something. Let's print the other parts. I have yet to see one of these time lapses. Okay. What is next? The next basic mechanism is, oh, this one's going to be hard, I feel like.
When rotary motion must be transferred from one end of a shaft to the other, this is usually easy with a long enough shaft. But when the input and output shafts are not perfectly aligned, or when the alignment can change during use, a universal joint can help. A universal joint, or U-joint, basically allows a shaft to rotate with a bend in it, which can change the angle of the output axis as much as 90 degrees in any direction.
How the fuck does that work?
A U-joint won't change the direction of rotation, speed, or torque, but it is a relatively inefficient mechanism and can cause power loss between the input and output shafts. U-joints are commonly found on drive axles of cars and trucks, which connect the spinning transmission to the drive axle. This socket wrench set uses a universal joint to loosen bolts in hard-to-reach positions where the wrench won't fit straight on.
Simple.
I don't get how it works, though.
Hello everyone.
Oh, give me a
In this
break.
session, we are going to link Unit 4 starting design, creating scheme, draw this. Make midpoint constrained to these lines. Change the dimension of the line, 57 millimeters. And this line is 18 millimeters. And this line is 16 millimeters. Draw a line connecting 57 millimeters line and 40 mm circle. Trim the unwanted lines.
How did they do that?
Trim the unwanted lines.
I have never ever used that. That is so useful.
Extrude this profile for 84 millimeters. Make the sketch visible. And extrude this profile, having offset length of 70 millimeters, and extrude distance of 14 millimeters. End operation as join. Again extrude the same profile for 14 millimeters, operation as join. Hide the sketch. And create sketch in this face. Draw a circle of 57 millimeters, 30 millimeters, and a rectangular of 7 millimeters and 8 millimeters, like this. Make this distance between these 2 points as 42 millimeters. And make horizontal vertical constraint with these 2 points. And extrude this profile for 38 millimeters, operation as join. Hide the body and make the last create sketch visible. And extrude this profile for 80 millimeters, operation as new body. And extrude this profile for 60 millimeters, operation as cut. And extrude this key profile for 57 millimeters, and operation as new body. Make all the body visible, hide the sketch. And create sketch in this face. Hide all the bodies. Draw a circle of 32 millimeters and 16 millimeters. And extrude this profile of 56 millimeters, and operation as new body. And create sketch in the front plane, and draw a circle of 32 millimeters and 16 millimeters. Make distance between these 2 points as 18 millimeters. And this line to this point is 28 millimeters. 32 millimeters and 16 millimeters. Make distance between these 2 points as 18 millimeters. And this line to this point is 28 millimeters. And extrude this profile, having symmetric direction, whole distance of 56 millimeters, operation as join. Select these 2 faces and delete. Make visible the body 1, create sketch in this face. Draw a circle of 16 millimeters and 25 millimeters. And hide all the bodies. Extrude this profile for 9 millimeters. And make visible the sketch. Extrude this profile for minus 96 millimeters. Operation as join. And extrude this profile, having offset length of minus 84 millimeters, and extrude distance of minus 10 millimeters, operation as new body. Hide the sketch, and construct a plane, form front plane, having distance of minus 15 millimeters. Create sketch in the created plane. Draw a circle of 4 millimeters. And having a distance between the circle and this center point is 89 millimeters. And make horizontal vertical constraint. Construct a plane form front plane having distance of 15 millimeters.
This video is actually crazy.
Created plane. Draw a circle of 3 millimeters. And having a distance between the circle and this center point is 89 millimeters. And make horizontal vertical constraint. And using loft comment, select this 2 profile and create loft. And operation as cut. Repeat the same procedure, make visible the sketches. And create loft operations as new body. Hide all the sketches, make all the body visible, and rename those bodies for identification.
So if it's bent at 45 degrees, it's that interface there that really does it.
Isolate the shaft, and create chamfer to the shaft. Unisolate the shaft. Select all the bodies and convert to components. Using move, copy comment, select the components expect center block, select create copy and move to the opposite side, rotate the components to fit with the original components, by following these steps. Go to modify, and select align, using this comment, align the copied components to the original component, by following these steps. Press right click and drag up for redo comment.
Okay. Dude, this is going to be a hard one. Maybe
Capture
I'll do this
position.
one later, because this is a hard build. Plus, how do you make it? I saw one on Thingiverse. Sort of a different design, but that will work. Is this an assembly instruction? What the hell is this? Hmm. Oh, acetone? Really? I didn't love all those answers, but whatever. Okay, what other ones can I do?
Simple gears use a rotary motion input to create a rotary motion output. In a two-gear setup, the direction of travel for the input will be opposite for the output. However, adding an idler gear can be used in the system to assure the input and output are moving in the same direction. This will not affect speed nor torque, as all the idler does is change the direction of rotation. To increase the speed of an output, a larger gear would need to be used for the input and a smaller one for the output. This also decreases torque. If this is flipped, a smaller gear for the input and a larger gear for the output,
Okay, so
speed
I think I
decreases
will
and torque increases.
try to build this. I won't build that part. Okay. Oh, is that like the new version that opened up? I can't believe I didn't get this rotation thing. Cause I never really know what you're thinking about.
Compound gears use multiple gears on the same axle
How does he
to take
space
a
it?
rotary motion input and create a rotary motion output. The direction of travel for the input will be opposite for the gear on the next axle over, but every other axle has the same direction of rotation. To increase torque, a smaller gear on the first
Okay. Yeah. There's one there too. There might be one there. I don't think there's one there though. It would be nice to have that railing. Um, bro, I swear. Okay. So let's just think about what that is. So if I were to build this out of 3D printing, just a housing. Oh, but you know what? I could make yeah, but you can't do self-tapping with plastic. Like PLA would just blunt. It's not gonna do anything. I'm trying to think of a way to get those spacers in there and use just oh, but you know what I could do? I could use normal screws and then just have a diameter slightly less, so then it self-taps. I think I'll try that. Not a bad idea. But then I gotta find some screws that. Okay, that's not a big deal. I don't know what you call this, a truss? What's the definition of truss? A truss is an assembly of members such as beams connected by nodes. Okay. So I think it does qualify as a truss. All right, so what is the basic shape? Gosh, this is going to take me. It's the same setup. Okay, so. All right, so. Oh, shit. So let's go back. This is probably the best picture of it. Let's just start. I don't give a shit. Okay, so. Okay, so the first thing is there seems like there's an L here. Or it's really like a, like half of an I. So it looks like it's like this. What is that? Oh, that's annoying. So the first part sort of looks like this. And that's just, or yeah, okay, then there's like a guy here and a guy here. Or actually, it's on the other side. And it's actually an L. And it's an L that way. So it's actually, dude, why is the delete key? Dude. There's so many UI things I hate about this program. Okay, so it's actually like this. Fuck. Maybe it's over-engineered to do that. Maybe I should just build another wall with pins in it. I do want a handle, though. A handle would be nice. Okay, well, let's just say we extrude this up by 5. That's not enough. 10. Why is it red? All right, you know what? I'm just going to commit, and we're going to build this. I don't care if it takes a lot of filament. I feel like the truss is the hard part, actually. So, yeah, so it's going to be like this. And then I wonder if you can 3D print these little things. What are they called? I wonder if you can 3D print shaft collars. You probably can. 'Cause I never. Okay, I don't think I need. Let's see. It would be nice to have all those holes, I guess. But what is the simplest truss that I could build? Because I'm going to need to print a lot of screws. I mean, damn, this thing is over-engineered. I mean, those must be like 4 or 5 millimeters. Probably 4. Bro, my God. Okay, so maybe I'll just build. I'll build it weak. So instead of really modeling out every part, we could have. What? This is probably going to be. God, already that's a lot of material. Then I don't know. We could build a part that's like. It's like this, where it's like. Fuck, I don't want that. But. So then you fit it between, well, I should have made this. Okay. So then if we have something going across, we can just draw a rectangle. Oh wait, what we can do is... Oh, that's annoying. Oh yeah, but I get it. Okay. No, I don't really care, but... What else needs to be... Yeah, that's fine. Okay, I don't really care. So we extrude these by, what was it, 100? So now we'll draw a sketch on there. I could just build it as a big U. No, but the problem with that is then you don't have the beams for like the actual gear compounding. Like, you do want some space horizontally. Okay, well, let's just go with that. But these are all part of one body. But the idea was... The idea is really... I forget. Do I have it? Nuts and bolts, maybe? Okay, yeah. So I wonder if I can just use these parts. Okay, I'm gonna get some food. Actually, how long is this thing? It's probably still got 20 minutes, 7 minutes. Okay. Okay. Oh, wait, this is supposed to go the other way. Okay. Bro, I want to watch this guy go in from the beginning.
Hi everyone.
While I eat.
Today's video is for people who have figured out how to make moderately complex parts in Fusion 360, but who are struggling with assemblies. And I find that this is also common among people who are coming from other CAD systems, because Fusion 360 does do a few things a bit differently. In this video, I want to show you how to model this thing right here. This is the pump module from the Polyvent project. It uses a stepper motor up here to turn this lead screw. And as that lead screw is rotated, this plate here moves. Hi, in today's video I would like to talk to you about gears. Now, I have quite a lot of material I wish to cover, so this will be a multi-part series. In today's part, I would like to show you how you can design a basic involute spur gear, and I want to focus especially on some of the techniques that you can use to attach 3D printed gears to your shafts. The current plan is that in the next part I will talk about the parameters and the numbers related to gears. For example, what is a pitch diameter, what is a diametral pitch, what is a module, and what number should I select for the various parameters for the gears that I need for my application. In another video, I want to talk about how you can model these helical and herringbone gears, and what are the advantages and disadvantages of these gears compared to regular spur gears. And then finally, I wish to discuss how you can design racks, including helical racks, and ring gears, including helical ring gears. So with that, let's hop into Fusion 360, and let's get to designing this gear. I've now opened up Fusion 360, and the first thing I will do is make the basic spur gear shape. And to do that, we'll go to Tools, and under Add-ins here, you go to Scripts and Add-ins, and then this dialog pops up with a bunch of scripts that are already installed. And if you scroll all the way down, you will find two instances of the spur gear script. As far as I know, it does not matter which one you pick, so you can just click Run. And
I
then
should
this
really
dialog
look
comes
into
up,
the
which asks for a bunch
documentation
of parameters for your gear. I will explain what all these parameters mean in a later video. For now, I will just pick a few parameters that will make sense later. For the module, I will go for 2.5, and I will design a metric gear with a pressure angle of 20 degrees. Number of teeth, 20. Backlash, I will leave at 0 for now. A root fillet radius of 0.5 millimeter. I want my gear to be 20 millimeters thick. And I prefer to make the hole myself later on. You will see why that is at that time. So I will put the hole diameter to 0, so that no hole is generated.
Yeah, okay, you
And at
just
the
set
bottom
it to
now,
0.
you can see that it gives a pitch diameter of 50 millimeters.
I was thinking, like, well, whatever. Like, you should be able to give a DXF, or you should be able to specify a custom geometry in there. I guess you just do it later.
This number and this name will become important in the next video, so keep that in mind. With all this entered, you can press OK. And then we get a new component, and this component is now our spur gear. What I'd like to do now is design the mounting hub for this gear. And to do that, I will first activate the new component that we just got, and then I will go to Solid, Create Sketch, and then click on the top surface of this gear. I then hit C on the keyboard for circle, and then from the origin I drag out a circle, and let's say we make it 30 millimeters. But I am going to 3D print this gear, and I want this mounting hub to be as strong as it can be. So instead of giving it a fixed dimension, I will just delete this. What I will do instead is select this inner little edge right here on the inside of the gear teeth, and hitting Control, I also select the circle that we just made. And to those two edges, I apply the equals constraint. And this now makes the mounting hub as large as it can be without interfering with the gear teeth. So I finish sketch, I hit E for extrude, and then I will extrude this 20 millimeters upward. Next,
Bro, this guy is so good.
To go into.
The way he does it, Antals. Dude, he's fucking... He just does it
For that, I will
well.
create a sketch on the top surface of the mounting hub, hit C for circle, and then from the origin I draw a circle of 8.2 millimeters. In my case, I want to mount this gear on a motor, and that motor has a shaft diameter of 8 millimeters. I also know that my printer tends to print holes that are slightly smaller than they need to be, and so to compensate for this, I make the holes just a little bit larger in Fusion 360. Hit enter on this, finish the sketch, then hit E for extrude, and then you could extrude this downwards to the exact length that you need for the shaft length of your motor, but you can also go the lazy way and just extend it all the way. And then press OK, and now we have a hole for our gear. The next thing I would like to do is make a cavity for a nut to go into. So I create another sketch on the top surface of the mounting hub, and then I hit R for rectangle. I drag that out, and then I hit D for dimension, and I will give this a dimension of 5 millimeters plus a little bit of play, and 10 millimeters plus a little bit of play. And these are the height and the distance between flats of an M6 nut. Next, I hit X for construction geometry and L for line, and from the origin I will drag out a horizontal line with a distance of 5 millimeters. And finally what I'll do is I will select this line of this rectangle, and I will select this point, holding down Control, and then to those two objects I apply the midpoint constraint. And then I can finish the sketch. I now this point, holding down Control, and rectangle. And finally what I'll do is I will select this line of this rectangle, and I will select this point, holding down control, and then to those two objects I apply the midpoint constraint. And then I can finish the sketch. I now hit E for extrude, and I drag down this profile by 10 millimeters. If you want to make it a little bit more parametric, what you can also do is construct a midplane between the top of the mounting hub and the start of the gear teeth, and then extrude up to that midplane. I'll leave that up to you. The next thing I want to do is create a hole for the set screw to go into. So I will now select this surface right here, create a new sketch. I hit C for circle, and then I will drag my cursor along this line until we see this little equilateral triangle appear. This is an automatic midpoint constraint, which I do want here. So I click and I drag that out and I type in 6.2 millimeters. That is more than enough to fit an M6 set screw. Finish the sketch, hit E for extrude, and click both of these profiles. And I want to extrude this in two directions. So under direction, I go for two sides. And then on the one side, I simply want to extrude it all the way. And on the other side, I want to extrude it 5 millimeters, which is exactly the same as the 5 millimeters that we had on the length of the construction line before. This extrudes it to exactly the center of the shaft hole. What you can also do, again, if you want to be a little bit more parametric, is instead of a fixed distance, you extrude to an object, and then you extrude to this plane here. And then click OK. And then we have a hole for our set screw to go into. The final thing that we will need is a little bit of a pocket for the nut to go into. And for that, I again click this surface over here, create a new sketch. And what I will do now is under Create, Polygon, take a circumscribed polygon, and then you want to look around here until you get this concentric constraint on the circle that we made before. So I click and just drag this out. The dimension that you get here doesn't matter, but you must here have a 6-sided polygon. You must have a hexagon for a nut. So I just enter that. And what I will do now is remove this dimension that I do not want. I will select this point here in the corner, and I will select this edge over here, and I will give that a midpoint constraint. And then I finish the sketch. I hit E for extrude. I select this profile right here. I drag that out in this direction. And then I want to take as an extent to an object, which is going to be this surface over here. And so that makes the bottom of the cavity hexagonal and with the exact same dimensions otherwise as the pocket that we already created. So click OK. And then we have all the features we need. We have a hole for our shaft, we have a hole for our set screw to go into, and we have a cavity for the nut that will accept the set screw. One final thing that I'd like to show you is how you can export this gear as an STL so you can 3D print it. There are two ways to do this, but one way is pretty terrible. The terrible way is to first save your gear, so let's call it video gear. And then once it is saved, you can go to File, Export, and then if you scroll down a little bit on the file type, you can export it as an STL. And then you get this cloud translation, which may take a few minutes and all that good stuff. So we export it, and then we have to wait for this to finish. This is the terrible way. The better way to do it is to simply go under Tools, under Make, and then 3D Print. And then in this dialog, I prefer not to send it through to a 3D print utility. The reason for that is every time you do that, a new instance of Cura is opened, and that leads to a lot of instances of Cura at some point. And then I select the component I wish to 3D print. You can also select bodies if you prefer. And then I hit OK. And then I can just save this. The file name is already set to the name of the component. I can save it, and then it's immediately done. And if we go to our job status, we see that this exporting via cloud translation is still going. I've now opened the gear in Cura, and there are two things here that I wish to show you. First, with the orientation of the gear like this, with the mounting hub on top and the teeth at the bottom, I can ensure that this entire gear can be printed well without the requirement for any support. Second, I have chosen to use 4 perimeters here. And what this allows us to do in the case of this gear with these size teeth is that the gear teeth consist nearly entirely of perimeters. And this gives a maximum amount of strength to the gear teeth. If you have larger gear teeth, meaning that the module of your gear is larger, you may need to increase the wall line count, or alternatively you have to print with fatter lines. So the line line width has to go up, and possibly your nozzle diameter has to go up as well. I would now like to show you how you can put this gear on a shaft. So we take the gear, and we take care to align the whole of the set screw with the flat part of the D shaft. And with that alignment ensured, we push the gear over the shaft, and then we take an Allen wrench and a set screw, like this, and then we simply drive the set screw into the hole. And with that, if we turn the gear, we notice that the motor also spins, so the gear is now rigidly attached to the shaft. I would now like to show you how you can design basically the same gear, but without a mounting hub, which makes it a little bit more compact. So I make a new design, and then I go back into the gear generator, and then I add the same parameters that I used before. So a module of 2.5, 20 teeth, a half, 20, and 0. And there we have the same gear as before. I activate this component, and I create a sketch on the top surface, and then I create the same circle as I did before of 8.2 millimeters to go over the shaft. Finish the sketch, hit E for extrude, and then extrude this all the way down again because I'm lazy, I don't want to match it to the shaft length of the motor. And then we get to a little bit of a different part. So again, we create a sketch on the top surface, and what I want to do is create the pocket now for the nut to go into. So I hit X for construction geometry and L for line, and I drag out a horizontal line here. The length doesn't matter. Then I create a second line from the origin, and I want to give that a length of 5 millimeters. And then I want to specify the angle between this horizontal line and this new line that I drew here. So I select them both and press D. And then the angle that I want here is 360 divided by the number of teeth, and that entire thing divided by 2. And the reason I select this particular angle, and the reason I'm doing this in the first place, is because I want the hole for the set screw to end up where the gear teeth are not. So I want it to land right in the middle of this section here, so that it affects minimally the strength of the gear teeth. So now I create a rectangle, but if I create a rectangle the normal way, then I get these automatic horizontal and vertical constraints. So that doesn't work. So Ctrl Z to get rid of it. And what I'll do instead is just draw 4 lines. And what I'll do now is add the perpendicular constraint 3 times to 3 pairs of lines. And then I give it the dimensions as before. So this will be 10.2, and this will be 5.2. And then as before again, this line has to be on the midpoint of this point. So select them both and then midpoint constraint. And then the final thing that we need to do is select this angled line here and the top end of this cavity that we're about to make and make those parallel. Then we can finish the sketch, and then the same as before, extrude it downwards by 10 millimeters. From here, everything is basically the same as before. So we create a new sketch on this inner surface here. I hit C for circle, and I look for this midpoint constraint. I make it 6.2 millimeters. Finish the sketch, E for extrude. Again, 2 sides, and on the one side I will go for all. Look for this midpoint constraint. I make it 6.2 millimeters. Finish the sketch, E for extrude. Again, 2 sides, and on the one side I will go for all. And on the other side, I will go for 5 millimeters. And now the point of what we've been doing so far, if I just click OK, is that most of the hole that we've made for the set screw does not dig into the teeth of the gear. And if you did it the other way, then the hole for the set screw would dig right through this tooth over here, and that tooth would then become quite weak compared to the other ones and would be prone to breaking. So the final thing, as before, create a sketch here. We create a polygon, a circumscribed polygon. Again, look for this concentric constraint to make sure it is a 6-sided polygon, and then take this corner point here, this line here, give it a midpoint constraint, E for extrude, and then this profile, you go up to this face, cut it out, and then we have basically the same idea, but this gear is much more compact than the previous one. One thing that I neglected to show you before is how you can insert the nut into the pocket. Now, if the fit is quite loose, as in this case, then it'll simply drop in. But you honestly want the fit to be a little bit tighter than this. If the fit is a little tighter, what you can do is put the nut inside a pair of combination pliers. If you have a pair of parallel pliers, that would be better. And then leave a little bit of the flats sticking out of the jaw. You can then keep the nut upright as you insert it into the hole. Finally, if you need to drive the nut home to the bottom of the pocket, what you can do is grab a screwdriver and just tap it home with a hammer. And then that way, you can ensure that the nut goes all the way to the bottom of the pocket. You will damage your screwdriver a little bit, but this is a €2 screwdriver, so see if I care.
This method of attaching the gear to the shaft using only a single set screw does suffer from two downsides. First is that there is a lot of force on the nut, and that force is transmitted into the plastic. And because the surface area of the nut is rather small, this creates a very large amount of stress in the material, in the plastic. And as I've shown in my previous video, PLA especially is susceptible to a phenomenon called creep, and this will cause the set screw to come undone over time. Another problem is because we have only one set screw and we are only pushing into the gear from one side, we induce a slight asymmetry. I have hooked up the motor now to a power supply, and I will turn on the power supply, and you can notice that the gear will wobble, it will not run true.
Let's now modify the design of this gear to address the problems I have brought up. First, I will add a cavity for a washer to reduce the stress in the plastic and thereby reduce the creep that the plastic will experience. So I will create a new sketch and then put that on this face over here. Hit C for circle and then look for this concentric constraint, and then I will give that 20.2 millimeters. This is for 20 millimeter washers, and then I give it a little bit of extra space to ensure that I can push them in later. Finish the sketch, hit E for extrude. I will select both of the profiles, and then I will drag that out by 1.5 millimeters. This is a little bit more than the thickness of my washers. The next thing I will do is create a sketch on the top surface of the gear, and then I will hit P for project, and I will project that circular cavity I just made into my sketch. And then on the view cube, I hit top so I can get back into the correct view. I hit L for line, and I connect these two lines over here so that I can get a complete profile. I finish the sketch, I hit E for extrude, and I select these two profiles over here, and I drag them down. And I will drag them to an object, and that object will be this circle over here. And then click OK, and now I have a nice cavity for the washer to go into. The final thing I wish to do is mirror all of these features to the other side of the hole to balance out the forces and to prevent the concentricity error I talked about before. To do that, I will go to Create, Mirror, and then the pattern type will be Features, and the feature I want to mirror is both the washer features and this pocket feature and the hole, and also this feature over here. And then the mirror plane will be this plane over here. And so now every plane will be this plane over here. And so now everything is being mirrored to the other side. I click OK, and then I do indeed get everything twice. I have two cavities for nuts, I have two cavities for the washers, and now if I look at it from this angle, I have one hole going straight through the gear. So now I can add two set screws to balance out the forces that this gear will experience and thereby prevent the concentricity error.
I have now mounted this new design to the motor. As you can see, if I give this a half turn, you can see the set screw on either side. And I will now turn on the power supply to show you the concentricity error. So to my eye, the concentricity does seem to be improved, but as you can clearly see, it is still not perfect. And I think the reason for this is that the X gantry of my 3D printer, which is a CR20, is sagging slightly because the lead screw to support it is on only one side of the machine. The other side is essentially free floating, and so that side sags down ever so slightly, which causes the axes to no longer be perfectly perpendicular. In particular, this means that the shaft hole that we drill here, or that we print rather, is not completely perpendicular to the faces. I would now like to show you a different way of attaching a gear to a shaft. This gear has a hole all the way through the mounting hub, and on the other side we find a nut, which will accept this screw. And what we'll do now is put this shaft through the gear, and then we have to line up the hole in the shaft with the hole in the gear. Now this is a little bit tricky to find, but if you cannot find it directly, you can use the pliers to give yourself a little bit more leverage. And once it's lined up, you can insert the screw and push it to the other side. And then once it engages with the nut on the other side, you can use an Allen wrench to tie the screw into the nut. And then we have our finished result. The benefit of using this technique is that you can transfer an enormous amount of torque through this system. There is no way for this mechanism to come loose due to a simple deformation. For this mechanism to fail, something has to break, either the shaft or the screw or the gear itself has to break into pieces, or otherwise this mechanism will stay intact.
We're now back in Fusion 360, and I've already designed some features of the gear. So the teeth are already there, I've already made the mounting hub, and I've already made the hole for the shaft. In this case, the hole for the shaft is 10.2 millimeters, because I want to mount this gear on a 10 millimeter shaft. What I'll do now is create sketch, and hit one of these vertical planes. I hit P for project, and I project this part into my sketch. I hit X for construction geometry and L for line, and I go from this midpoint here, upwards to this midpoint over here. I want a line going straight up. I disable construction geometry and hit C for circle, and I look for the midpoint of the line that I just made, and I give that a diameter of 4.2 millimeters because I want to put an M4 screw through it later on. I finish the sketch, I hit E for extrude, I go to two sides, and then on both sides I will select the extent all. And then it bugs out, it unselects the profile, so just select it again, and then press OK. So now I have a hole through the mounting hub of my gear. I'd now like to add a small cavity for an M4 nut to seat into. To do that, I will first construct a tangent plane, and the plane will be tangent to the mounting hub. And for the reference plane, I will unhide the origin of the gear, and then I will select this plane. And this will ensure that the plane I am constructing is perpendicular to the hole. Then I create a sketch on this new plane, and as before, I hit P for project to project the gear into my sketch. And as before, I can't really select an automatic concentric constraint here. So again, I press X for construction geometry and L for line, and I draw a line like this. And now what I want to do is go to create, polygon, circumscribe polygon, and then from the midpoint I draw out a polygon like this, again 6-sided. The distance between flats now is 7 millimeters. You want this to be quite tight. You can force the nut in, and then it'll stay there due to friction. And then to constrain it fully, we select one of these edges and give it a vertical constraint. Then we finish the sketch, we hit E for extrude, and then we extrude this inward by about 5 millimeters. What I'd like to do now is make a pocket for the head of the screw to fit into. To do this, I create another tangent plane, tangent to our mounting hub, and then the reference plane will be this plane that we made before. And for the angle, I will give it 180 degrees, so it ends up exactly at the opposite end of the mounting hub. Now we create a sketch onto this new plane, hit P for project, and now I want to be a little bit more careful with what I select for projecting. So I'll select this line up here, and this little line down here. And the reason for that is that otherwise I get too many profiles that are available for extruding, and then I have to go through the effort of selecting the right ones. So hit OK, and then on the view cube I just hit left so I can get a better view again. X and L for construction line, and draw that up like this. Then disable construction, C for circle, and I'll make this circle 7.5 millimeters thick because it's better if the screw fits quite loosely in here. This doesn't need to be tight. Then hit E for extrude, and then extrude the entire thing 6 millimeters down because the head of the screw is a little bit thicker than a nut. Hit enter, and there we go.
One of the difficulties in using this technique is that you must drill a hole through the shaft that is central on the shaft. It must not be off-center because then the alignment won't work. And this is more difficult than it seems because as you try to press the drill bit into the steel, if you are off-center ever so slightly, the drill bit will tend to wander off that way or the other way. And so getting this hole nice and centered is quite tricky indeed. For this, I have designed a special jig. And this jig consists of a lower and an upper part. And then on the bottom end here we have some nuts, which we will use later for clamping. And then we just add the steel shaft in this little channel. And then we put the top half on top. And then we can simply use some bolts to close up the jig. I've now closed up the jig, so we have the bolt heads on top, with the nuts here on the bottom. And in the center now we have the shaft. And on the top end here we have a small little hole which will guide the drill into the shaft. So we can now put this on the vise and close it up. And now we can start drilling. So I now try to locate the hole with the drill bit and then push it down. And now the jig will guide the drill bit centered on the shaft. So we now have a completed hole, but there is now a little downside to the jig. And that is that the chips that have been evacuated by the drill bit upwards into the jig have now enlarged this hole substantially. And so now the top half of this jig is not really usable anymore. So here's a previous one that I used before, and you can see this one is also not usable anymore. But now let's open up the jig and I'll show you the result. So I've removed the bolts, and here we have our result. You can see that the hole is nice and centered on the shaft, though you should note that because I was slightly careless, the two holes now that are in the shaft are not exactly parallel. Nevertheless, both of these holes should work for mounting this gear, so let's give this a try. And I will grab my wrench, my pliers rather. Put this in the right position. And now I should be able to ram the screw in there. Grab the Allen wrench, and you can tighten this down. You may have noticed over the past few shots that the screw of this gear is a little bit too long. But I would like to point out that the reason for this is because this screw has a piece of smooth shank. And it is this smooth shank that is in contact with the shaft, and this ensures a higher amount of strength and also provides a little bit less backlash. But what I want to do now is cut this screw off to the correct length, and for that there is another special trick. So I will make a mark where I want to cut the screw off, and then I'll go cut it. So I've put the screw in the vise now, and you can see the cut mark right here that I want to make. And on the other end of the cut mark, I've inserted 3 nuts, and the reason for that will become apparent in just a second. So now I've cut off the last bit of the screw that I do not want, and if I open up the vise and you look closely at the thread, you can see that it is slightly damaged. And the nuts now will act as a sort of die to reform the thread into what it needs to be. So this basically undamages the thread by unscrewing these nuts. And it gets easier for the third nut than it was for the first. I'm not completely happy yet with this screw because there's a slight sharp burr here that I want to remove. So I've put 2 nuts again on the threaded section, and I can just take a file and get rid of that little nubble that I do not want. So that's smooth now. And then I can take the screw out of the vise again, and again threading the nuts back over the piece of thread that I just damaged. This doesn't work. So I will need to use my pliers instead. I misspoke, of course I'm not going to use my pliers, I'm going to use my vise. Now this should fit nicely into our gear. So here we have our gear. Put the screw in like this. Take our wrench, and we can turn it in. And now we have everything we want. The screw is no longer proud of the mounting hub. The head of the screw is also nicely inside the mounting hub. And here we see again that the smooth shank is in contact with the shaft. And this again ensures the maximum amount of allowable torque and also reduces the amount of backlash. I hope you found that interesting and informative. In the next video, we'll be taking a look at what parameters you need to select for your gears. And one example we'll cover is this Archimedes screw pump. Now, in today's video, we've designed this gear over here, but the action of the pump is done with this shaft down here. And what we want to do now is connect this shaft to this motor via 2 gears over here, so we need to design the matching gear for this gear that we already have. I'd like to thank you very much for watching. Don't forget to hit one of those buttons on your way out, and have a great night.
Hi, in today's video I would like to cover 2 topics that I couldn't quite cover in my last video. I would like to show you how you can model compound gears, and I would like to show you how you can add chamfers to the teeth of your gears. I have opened up a new file and I've already created the first gear. I will now go back into the gear generator and generate the second gear. This gear will have many fewer teeth than the first gear, and for demonstration purposes I will also make it slightly thicker than the previous gear. And then we press OK, and then our second gear shows up. Now that we have 2 gears, we must combine them into becoming a single gear. So first we go to Solid, Modify, Move Copy, and what we will move is a component, and in particular it will be this smaller gear. And then we move that up by 20 millimeters, which is exactly the same as the thickness of the bottom gear. Next, we go to Modify, Combine, we capture the position, and the target body will be the lower gear, and the tool body will be the upper gear, and the operation will be join. So click OK on this. And now if we look inside of our components, we see that one component has one body in it, which is our combined body, our complete compound gear, and the other component only has the origin and a few of the sketches. So this component is no longer necessary, so we can remove it. There is one unique aspect of compound gears that I would like to discuss. Most gears need to be fixed rigidly to their shafts because they need to be able to transmit torque into or out of that shaft. Compound gears do not need to do this, and so these must be mounted in a way that they can rotate freely with minimal wear and friction. This is most commonly done by mounting the gear to a shaft and then having that shaft rotate between 2 bearings. But I'd like to show you a different technique, and in this case the shaft is held stationary and the gear will rotate around the shaft supported by 2 bearings that are mounted inside of the gear. So we create a sketch on the top face of the gear and we will drag out a hole of 22 millimeters plus a little bit of space. And this is for a 608 bearing. Now you can of course use whatever bearing you like, but I'll just take 608 for now. I hit E for extrude and I pocket this down 7.5 millimeters. It's 7 millimeters thickness for a 608 bearing, and I give it a little bit of extra space to ensure that the bearing is not proud of the face of the gear. So we hit OK. And now we want a similar pocket on the other end of the gear so that we can have a bearing there too. So we construct a midplane and we select the 2 gear faces. And then we go to Create, Mirror, and then we mirror a feature, which will be this pocket, and we mirror that around the plane that we just created, and we press OK, and then we have another pocket for another bearing. The final thing we'll do is there too. So we construct a midplane, and we select the two gear faces, the plane that we just created, and we press OK, and then we have another pocket for another bearing. The final thing we'll do is create a hole for the shaft to go through. Now, we only want the shaft to touch the bearings, but not actually the gear itself. So this shaft actually needs to be a little bit larger than the shaft to ensure that there is no contact. So the 608 bearing is meant for an 8mm shaft, so I will make this hole 10mm to ensure that there is no contact. Finish the sketch, hit E for extrude, put that all the way, hit OK, and there we have a finished gear. The advantage to this technique is that you no longer need to create space for the bearings inside the housing of your gear train, and this allows you to make the housing a little bit more compact. The downside is that instead of the inner race, the outer race of the bearing is now rotating, and this causes the RPM limit of the bearing to be a little bit lower than the specifications would imply. However, usually I don't get anywhere near the RPM limit for a bearing anyway. I'd now like to show you two different techniques for adding a chamfer to the teeth of your gear. For the first technique, I've already created the gear in a generator, of course. We'll start with a sketch on this vertical plane. And first, I project the top and bottom surfaces of the gear into my sketch, using P for project. And then I draw a construction line going from the origin upward, and I'm looking for this perpendicular constraint. And then from the middle of this new line, I draw a horizontal line going straight out, and the length of that line doesn't matter. Next, using regular geometry, I draw a triangle like this, and I'll just give this some dimensions. Now, I don't want the chamfer just on the top face of the gear, I also want it down here on the bottom. So to achieve this, I will go for a mirror and select this triangle, and the mirror line will be this line that we made before, and then we press OK. And now these two triangles can still move around. So what I'll do first is select this top edge and select this projected line and make these collinear. And now the only degree of freedom we have left is this side-to-side motion. So one thing you could do is make this point coincident with this point. But if you zoom in real deep on this area over here, you see that there are in fact 2 points very close to each other. So you run the risk that you would select the wrong one. So another way to do it is to select this edge over here and this central line that we drew before and set the distance between those. Now what must that distance be? Well, it'll be the module, which is 2, times the number of teeth plus 2. And that gives you the outer diameter of a gear. But we don't want the outer diameter, we want the outer radius. So we divide the thing by 2, and then the triangles are at the correct spot. Now we can finish the sketch, and then we go for revolve. And then the profiles will be both of these triangles, and the axis can either be the z-axis or this construction line that we made before. And then we hit OK. And then we have a chamfer that is a lot like the chamfer that a machinist would make into a gear using his lathe. I've now added a second gear to the design, so I can show you the other technique. And for this, we simply go to the chamfer tool, and then we rotate our camera around a little bit like this, so we can draw a box that selects all the top edges of the gear. And then we do the same thing to select all the bottom edges of the gear. So we now have 100 edges selected, and we enter a distance, let's say of 1mm. And this takes a little while to compute because it's quite a difficult geometry for Fusion 360. We hit OK, we wait again for a little while. And there is the second chamfer complete. Now, why would you want to add a chamfer to the teeth of your gear in the first place? And I can think of 4 reasons. First, if I delete this chamfer on this gear, and we imagine that these gears are made out of hardened steel, then this area over here, near the corner of the teeth, has a tendency to chip off. And one of the ways to prevent that is to preemptively remove the material, basically, by adding this chamfer. And a hardened steel chip inside your gear train will reduce its life very quickly. The second reason is that if you try to push these gears into mesh, these chamfers will help the 2 gears find each other so that they will go into mesh. Third, if you use the technique on the right here, the chamfer counteracts the effect of elephant's footing in your 3D printer. So if your printer suffers from a little bit of elephant's footing, then these edges over here being a little bit too wide will cause the mesh of the gears to be quite a bit worse. And you can counteract that by adding the chamfer that you can see on this gear. And finally, as this old Tony teaches us, the chamfer makes the gear look a little nicer, and you can charge more for parts that look nicer. I hope you found that interesting and informative. Thank you very much for watching, and have a great day.
Hi, in today's video I would like to discuss some of the parameters and some of the basic mathematics involving spur gears. I would first like to start with the absolute minimum requirements that you must meet for 2 gears to mesh in the first place.
If you find yourself repeatedly performing the same sequence of actions in Fusion, I want to tell you about a plugin that I use called Any Macro. Any Macro allows you to record a sequence of up to 10 actions and then play them back at any time via a custom button placed on your toolbar. One example of how I use Any Macro is to create a simplified primitive as a bounding box of my original part body, and I'll show you how I do that right now. Okay, so with the part file open, I'm going to head to the Utilities tab, and I have a button that says Any Macro. When I press this, it will begin recording all of my actions. So in this case, I'll copy this body. I'm going to turn this body into a simplified primitive. I'm going to set the opacity of this primitive to 25%. And the last thing I want to do is create a rigid group between both of those objects. And we're done. So I'll head back to the Utilities tab and stop that macro. Now, if I click on the dropdown and look at Macro Recorder, you can see all of the actions that I just recorded. I can go ahead and save this primitive from body. And now again in the dropdown, custom macros, primitive from body. And now I can select these three dots and pin that to the toolbar. So now this button will run that macro. And we're going to do that right now. I'll delete that primitive and this body, and we'll run the macro. So it says copy this body, turn this one into a primitive, change the opacity on this one to 25, and create a rigid group between those two objects. All right, so that is Any Macro. If you are curious,
Hello, greetings. Hello, hearty salutations. Welcome to Tech 3D, where we are back with tutorials. I'm excited. Right, if you want to follow along with this tutorial, which is the Fusion Automate command, you want to use the same files as I'm using, they're available as part of Tech 3D. Join membership on YouTube. My entire tutorial, data file, all files, past and present, and future, will be available for download as part of the Tech 3D membership plan. Alternatively, you can just follow this along using your own file. Apparently in the future. So they say, I'm using the Automate command. Automate is a sibling of generative design. The short video necessarily is the same sort of thing as one version of that short video. It's a sibling of generative design where it'll create geometry and make a part design in between faces that you tell it to do. Right? But it's not generative design is a lot more intelligent. It's basically doing it for you for all intents and purposes. So you select the faces that you want to make material between. So say that face there, and it'll start generating geometry between those faces and these ones here. So it can be this weird alien structure sprouting out from the faces and then joining all together. And then it's up to you. There'll be three alternatives. It's actually six, but basically three. You can tell it to either make that material as a new body within the Fusion component, or a new component which would be like a part in an assembly, which is a fair question to ask because you might want this to be a completely new body, but I actually want this to be a body. It's going to be part of the same. If it's a wheel, it's all one molded or forged piece. So we want that to be a new body. But you've also got bodies to avoid, and this one is where you can make this really creative because when you don't have bodies to avoid, it's going to spawn material just anywhere it wants to go. But you might say, well, don't put material in a certain place, and you can almost sort of dictate the navigation of the new stuff. So we're going to select we'll create a sketch plane, and then let's do polygon. Why not? How does Fusion polygons work on three sides? Can I just type in 3? No, I can't. Okay, brilliant. Why can't I go to that? There it is. Edge number 3. So we'll do a triangular about here. That's it. I don't care about the size. I'm not too fussed. I'm not even fussed about the shape, to be honest. And the position. I want the position though to be on that center line. Why not? So now, when the material spawns out from this face and this face here, I want it to avoid a body of this size and position. So let's go to extrude that. We'll go to a symmetric extrusion, and we'll just say boosh. There we go. So it'll have to dodge that area when it makes the new material. It doesn't have to be a triangle, right? It can be any shape you want. You can define tires.
Compound gears use multiple gears on the same axle to take a rotary motion input and create a rotary motion output. The direction of travel for the input will be opposite for the gear on the next axle over, but every other axle has the same direction of rotation. To increase torque, a smaller gear on the first axle can connect to a bigger gear on the second axle. This second axle can
to create the hex nut. From the center origin, I'll type out a radius of 12 millimeters. Now you can also clear out the command with the escape key, select the horizontal constraint in the toolbar, and then select an edge. This will make sure the sketch is fully constrained. We'll also need to create a 16 millimeter center circle for the internal thread. For the height of the nut, I'm going to extrude this to 8 millimeters. The next step would be for us to apply the internal thread to the nut. To do this, we can activate the thread feature and simply select the inside cylinder. Once again, Fusion 360 will automatically detect the closest thread type. After confirming that it did detect the M16 thread that we're going for, we can click the OK button. At this point, we can take a look at the section analysis to see how much clearance there is between the two parts. From the Inspect dropdown, select the section analysis. Then simply click one of the vertical origin planes. If I zoom in, you'll see that Fusion 360 automatically includes a clearance between exterior and interior threads. This first threaded nut is going to be our first clearance test. By default, it has a 0.1 millimeter clearance. Depending on the size of the thread and the tolerance of your 3D printer, this default clearance typically needs modifications, but we'll use it as the start of our test. Let's make a copy so I can show you how to increase the clearance, which is typically needed before 3D printing on a consumer level printer. I'm going to shift click the two components in the browser. I'll right click to select copy, and then I'll right click on the top level assembly, which will let us choose the paste new option. It's important that you select paste new on types of 3D printing projects with Fusion 360 workflows that you find the most challenging. The easier is offset the thread faces based on your printer's tolerance components, or Q as in Quebec. Remember that this shortcut activates either the press bolt command or a negative distance to add a slightly larger clearance between this external thread and the internal thread of the nut. I want a total of negative 0.2 millimeters, so I'll offset this thread another negative 0.1 millimeters. We'll then need to do the same thing for the bottom. I'll select the bottom thread flank, hit the keyboard shortcut letter Q, and I'll type out the bottom. We'll then need to do the same thing for the bottom. I'll select the bottom thread flank, hit the keyboard shortcut letter Q, and I'll type out negative 0.1 millimeters. If you turn the copy nut component back on, you'll see that we now have a larger clearance between the two parts. Thread size, play, so on. Details. Highly recommend great way to use analysis command, and I'll select the clearance added to the default. Again, I'll extrude so we can do one more test.
Okay. I guess I was muted that whole freaking time. Fantastic. I'm pretty sure he does this too.
Test print. If you look at the thread, as we all know, most mentally plastic threads don't do well when they're very thin as they break down threads. We're nice round over to the edge of the to do that to this third model so we can compare the printed results. I'll hide the nut component so we can work with the edge of the threads. I'll then select the face of the edge before hitting the keyboard shortcut letter F as in Foxtrot for the fillet command. I'll add a fillet of 0.05 millimeters. As you can see, that adds a nice round over to each edge. However, when you think about it, and if we input a fillet, we're supposed to apply a greater fillet radius. I'll select the edge, and then I'm going to hit the keyboard shortcut letter Q. This time, I'll type a distance of negative 0.1. Before reactivating the fillet command, I'll select the edge again. This time, I'll add a fillet radius of 0.15 millimeters, which equals a total of 0.3 millimeters, something that will make a significant difference.
So then, what the fuck did I do wrong? Bro, how am I still getting this wrong?
Difference in the print.
That is insane that I'm not getting this. Why? Okay. Okay, yeah, I'm starting over. Fuck. Thread. This M16, yeah. That's good. Oh, shit. Thread. Wait. Can I get used to this thing? Okay, now we did this. We did Q minus 0.1. Okay, then we did this. Q minus 0.1. Okay, then we did this. Q 0.1. Wait. Okay. Now, if this fillet doesn't get rid of that stupid middle section, I'm going to freak out. Why, bro? Why? But there is that middle section. What the hell am I missing? And why does that look like crap? Maybe I should just save this component. No, I'm determined, dude. I gotta get this thing. This is so annoying. How did I mess this up so badly?
We also want to make sure to add the same radius to our internal thread of the nut. I'll turn the visibility of the nut. When you think about it, 0.05 is very small each edge. What we can do instead is offset the face of the edge first, which will allow us to apply a greater fillet radius. I'll select the edge, and then I'm going to hit the keyboard shortcut letter Q. This time, I'll type a distance of -0.1. Before reactivating the fillet command, I'll select the edge again. This time, I'll add a fillet radius of 0.15 millimeters.
Dude, I literally did exactly that. What did I forget?
This will ensure that we can create copies of the design so we can test the different clearances. Now you can however, I prefer the diameter in M16 hex bolts. Therefore, I'm going to make this 16 millimeters in diameter. For the length, you would set to create some text to tech thread. Select the face 360 will automatically cylinder. You will need log. We're also given, however, if you select this option, you can then drag the blue directional arrow with the offset from the nut. Create in M16. In this case, it was correct. However, you can also choose from several preset thread types based on the type of project your work or else resource number. If I switch this to 20 millimeters, you'll see that the designation switches to M20. For now, I'll switch this back to 16 millimeters. With the designation option, you can also define the pitch of the thread. The pitch of a thread is the distance from one crest to the next crest. Right now, the pitch of thread be used not working the thread is generally to fit size. We'll then need to create a new sketch off either the top or the bottom thread so that we can sketch a polygon for the nut. Origin range is fully constrained. We'll also need to create a 16 millimeter center circle for the internal thread. This simply detect between the two parts. From the inspect dropdown, select the section analysis. Then simply click one of the vertical origin planes. If I zoom in, you'll see that Fusion 360 automatically includes a clearance between exterior and interior threads. This first threaded nut is going to be our first clearance test. By default, it has a 0.1 millimeter clearance. Depending on the size of the thread and the tolerance of your 3D printer, this default clearance typically needs modifications, but we'll use it as the start of our test. Let's make a copy so I can show you how to increase the clearance, which is typically needed before 3D printing on a consumer level printer. I'm going to shift click the two components in the browser. I'll right click to select copy, and then I'll right click on the top level assembly, which will let us choose the paste new option. It's important that you select paste new and not paste, as you want us to create an unlinked copy so our first two components aren't altered. Now I'm going to drag the copies to the right, and then I'll click OK. Before we add additional clearance, I'd love to hear what types of 3D printing projects with Fusion 360 workflows that use ideas with command toggle with. Have a clearance option built into the thread command. Instead, what you have to do is offset the thread faces based on your printer's tolerances. I'm going to hide the copy nut, and I'll activate the copy thread component. We'll select the top thread flank, and then we'll hit the keyboard shortcut letter Q as in Quebec. Remember that this shortcut activates either the press pull command or the offset faces command based on our selection. We want to offset the face a negative distance to add a slightly larger clearance between this external thread and the internal thread of the nut. I want a total of negative 0.2 millimeters, so I'll offset this thread another negative 0.1 millimeters. We'll then need to do the same thing for the bottom. I'll select the bottom thread flank, hit the keyboard shortcut letter Q, and I'll type out negative 0.1 millimeters.
Dude, am I tripping or am I doing it right? I swear to God I'm doing it right.
Perfect clearance for your desired thread size and your 3D printer's tolerance. There are so many factors in play between 3D printers being different, setting up as thread even, select the top face of the thread component. I'd like to type out the clearance added to the default. 0.2 to make this. I'm going to copy the latest thread and nut, and I'll make sure to select paste new from the top level components. After dragging them over to the right, I'm going to turn the section analysis back on. I'll also make sure the thread component is active. If you look at the threads on most plastic parts, for example, the threads on a disposable water bottle, you'll notice they're almost always rounded over. As we all know, most metals are stronger than plastics, and they hold up better long term. Generally, plastic threads don't do well when they're very thin, as they break down and get gummed up to the point that they don't work, which becomes a serious issue with threads. Therefore, one of the things that you can do with your 3D printed threads is to add a fillet or nice round over to the edge of the threads. This will make them much more durable. We're going to do that to this third model so we can compare the printed results. I'll hide the nut component so we can work.
Bro, what the hell? Whatever, that should be fine. Okay, so now, what is it we want to do? On this top face, we want to draw, and then we want to draw, but we could just project this thing. We could just copy it. Create polygon, circumscribe polygon, boop, boop. Hello? Okay. Wait, let me go back to the nut part, because the nut part...
To achieve the same thing. To make this 16... Top of the dialog, as a lot of people looked over to note the threads in a 2D drawing happens as I 3D print.
Okay, here we go.
Of 12 millimeters. Now you can also clear out the command with the escape key, select the horizontal constraint in the toolbar, and then select an edge. This will make sure the sketch is fully constrained. We'll also need to create a 16 millimeter center circle for the internal thread. For the height of the nut, I'm going to extrude this to 8 millimeters. The next step would be for us to apply the internal thread to the nut.
Maybe 16. Okay, now we can select this. And this, when we do -10, there should be no cut that shows up right. Okay. So, and then he does new body. But I actually want to cancel this whole thing and do this. Okay, wait. So, new component. This is going to be the... oh, wait. No. This is called the bolt. And then we're going to create a new component called nut. Okay, and then this body goes into bolt. Okay, all right. So now we create a sketch, and then do we still have all of our shit? Whatever, I'm just going to do it again. Okay, then we do -10. That shouldn't have cut anything. Now if we hide this, we should get this. We can redo that, and we can do thread. And I think that was it, right?
To do this, we can activate the thread feature and simply select the inside cylinder. Once again, Fusion 360 will automatically detect the closest thread type. After confirming that it did detect the M16 thread that we're going for, we can click the OK button.
Oh yeah.
At this point, we can take a look at the section analysis to see how much clearance there is between the two parts. From the Inspect dropdown, select the section analysis. Then simply click one of the vertical origin planes. If I zoom in, you'll see that Fusion 360 automatically includes a clearance between exterior and interior threads. This first threaded nut is going to be our first clearance test. By default, it has a 0.1 millimeter clearance. Depending on the size of the thread and the tolerance of your 3D printer, this default clearance typically needs modifications, but we'll use it as the start of our test. Let's make a copy so I can show you how to increase the clearance, which is typically needed before 3D printing on a consumer level printer. I'm going to shift-click the 2 components in the browser. I'll right-click to select copy, and then I'll right-click on the top-level assembly, which will let us choose the Paste New option. It's important that you select Paste New and not Paste, as you want this to create an unlinked copy so our first 2 components aren't altered. Now I'm going to drag the copies to the right, and then I'll click OK. Before we add additional clearance, I'd love to hear what types of 3D printing projects with Fusion 360 workflows that you find the most challenging.
Bro, I am bugging out. How did this get messed up so badly? I mean, honestly, it shouldn't matter. Ay, that's so fucking lame. Okay, it shouldn't matter, though. The only thing we need to do is that offset faces shit.
Many of you have already commented with great ideas, but the more people that comment, the easier it will be for me to create content with the highest demand. Help me out by commenting down below with at least one 3D printing workflow that you struggle with. Select the corresponding. This time, I'll add a fillet radius of 0.15 millimeters, which equals a total of 0.3 millimeters, something that will make a significant difference in the print. We also want to make sure to add the same radius to our internal thread of the nut. I'll turn the visibility of the nut component back on, and I'll make sure it's active. I'll select the corresponding inner edge before once again applying a fillet of 0.15 millimeters. Last but not least, we also want to make sure to mark this third version so we can tell them apart.
Okay, so he only does the fillet. Wait, but...
Flank, hit the keyboard shortcut letter Q, and I'll type out negative 0.1 millimeter. See that we now have an error to find the perfect clearance for your desired thread size and your 3D printer's tolerance. There are so many factors in play between 3D printers being different, set that as threads get more, table them. I'll activate the text command, and I'll select the top face of the thread component. I'd like to type out the clearance added to the default. For this one, I'll type out negative 0.1.
Okay, so let's just do the fillet then. Okay, that should be fine. Okay, so now... Now we need an L to go like this. And we'll just mirror it. So this needs to be 17 then? Sure, let's just make it nice numbers. Okay. Actually, is there going to be enough clearance? Yeah, I know what happened. Is that I put the sketch on the wrong plane by drawing that L and extruding the L as opposed to drawing a rectangle, extruding the rectangle, and then drawing on the top of the rectangle. Okay, but regardless, what is the distance between here and here? 28. So we should have enough clearance to get the nut on. Okay, so let's... Oh, it deleted my extrusion. Fuck. So much nonsense in this program. Okay. Dude, I'm starting over. That was hell. That was hell with the rotation. Alright, so this is going to be... No, yeah. Okay. It's 30. Make this one 30 and this one 100. Okay, then we extrude this by 2. Let's make the wall thickness 2. Okay, then we want to draw on this face. We want to add our little L. So we want to do this to here, and then make this 2. Enter. Now this is all locked in place. And we want to extrude this 30. Is that right, or is that asymmetrical? Why doesn't it give me the face dimensions? It's so annoying. Okay, so we need to undo this. Actually, you know what we should do? Go back to this thing. Okay, wait. Sketch. We want to go back to this. Change this to be 32. Okay. All right, now they're both 30. Now we want to draw some circles on here. Sort of, I don't know. That should be fine, right? Okay, then this needs to be 17. This needs to be, this is going to be, yeah, 15. Right, so it's actually centered in this thing. And this is going to be 15 also. Okay, then we want to extrude this to object. Bam. Okay. I could have just put -2. Now let's make a midplane. Construct midplane. Select this thing and this thing. Okay. Now we do mirror. Okay. Now we do features. We want to select this feature, mirror plane, this plane. Okay. So now we have two things. Now what we want to do is we want to have, looking from this direction, we want to have an L that goes like this. So now if I were to create a sketch on this plane, I'm going to have like, let's make it 32, and then whatever it's going to be, yeah, 100. Okay, then 2, then, oh wait, well, we need the other sides. So this is going to be 30, it's going to be 2, this is going to be 30, this is going to be 98. Wait. What? Wait, hold on. From here, oh, it's going to be 96. Okay. So then this bracket is going to get extruded. And that, oh wait, I did this wrong. Bro, I gotta... Okay, so what it actually is it's not this. So let's just undo all this. It's here to here. Why don't I get a oh. This is gonna be 32 also. This is gonna be 90. Okay, then this way is gonna be 2. So it's gonna be 30. Fuck, what the hell? 90. And this one. Okay. What's wrong with this? Oh. Now we extrude this like 100, right? Okay, then okay, so it's, no, this needs to be shit. This needs to be a new body. So now we have 2 bodies, right? Okay. Can I extrude this? You can't really extrude it. Okay, so now we're gonna put a bolt in there. And then we wanna, okay. So these are identical parts, right? So I actually wanna, let's see if we can avoid building this whole thing. So can I just copy this? Copy. All right, if I make a new thing and I paste this. Paste. Dude, yeah, this program is so fucking bad. It's actually incredible how bad it is. Okay, wait. But what happens if I make a new component? I say. It doesn't even let me name it. Okay, fine. Let's. Yeah. Let's copy this and paste new. Okay, cool. Now we want to paste new again. And this one we want to rotate it like this and then rotate it like this. No. We need to flip it around, right? Because we want right, except now we need to rotate which one? This one, 180. Okay, perfect. Okay, now we want to join this. Oh, wait. It's so easy to get these J's wrong. So here, there's that. Why are you going away? Why are you hiding? Okay, and fine. And we can just move this minus 2. All right, I'm fine with that. Ugh, but no, why is that? I must have designed this wrong. Can I? Oh, it needs to be 16 actually. I wonder if it imports a timeline. Does it? Close that. Is this the right one? But do we get the whole timeline? Yikes, that's really annoying. The problem is that it's 15 away from there. Oh. But it's 13 away from there. Do we just extrude it? I feel like we just extrude it. I mean, at this point, I just want to print these. Okay, fine. So now I want to take this body. All right, wait. So we construct mid-plane between here. Yeah, okay, I think that's right. Wait, no, that seems a little off-centered. Oh, wait. Okay, now this body across there. A join. Yeah, okay, that's fine. That's a good warning. I understand what that means. Okay, so now the thing is, the distance between here and here It's only 36 millimeters, which is not that good. We actually want it to be more, probably. I mean, that looks like it's more than 3 centimeters across. But okay, but I want to try to insert the fastener. Can I just watch a video about this really quickly? Fasten nerds. Fucking got ya. Beat fastener. Okay, fine. I'll try this first one.
What's up, guys? Justin here with the Fusion Essentials. So in today's video, we're going to check out a brand new feature they just added to Fusion 360 that allows you to automatically add fasteners to objects. Let's go ahead and just jump into it. All right, so this is actually a really cool feature. So we've had access to like McMaster Car and other things like that in the past, but what they've just done in the newest version of Fusion 360 is they've added the ability to insert fasteners. And so what you can do is within this object right here, and I just created some random plates. There's no real like rhyme or reason to these or anything like that, but you've got the ability to click on this button right here to insert a fastener. Well, if you look at this, we now have a library of bolts, screws, nuts, and washers in here that you can add automatically, which is super cool. So let's say that we wanted to add maybe like a, we'll go with a round head right here, and we'll go with maybe a self-tapping, and we're just going to pick one of the options that are over here. So notice how you get a ton of different options in here for things that you can select. You can kind of move this out and move this over in order to see
What if I just try this? Insert fastener, hex M16. Is that gonna work? What if I just look up M16? Alright, whatever. Hex, square. Is there a hex? There we go. Hex head. Self-tapping. Sheet metal. Look, there's so many options, bro. Hex bolt. That sounds good. Yeah, that's... Wait, but what is that? Oy, oy, oy. Bro. This shit sucks, actually. What if I just search M16? Okay. Yeah, see, that's what I'm saying. This thing kind of sucks. The length, I said 24, right? Oh, of course not. We can't just put in our own length. That would be insane. All right, whatever. Let's say okay. Okay. So now we want to put this just say okay, and then let's J this. And what do we want to do? It's not actually that obvious. Okay, that actually seems pretty good. But now I need a bolt for it. How do I get the bolt for it? Or I mean the nut. M16 nut. M16 hex nut. Heavy hex nut. This shit's so annoying. Where did all these bodies go? Oh, they're in a specific fasteners thing. Okay. So let's J this bad boy to here. Okay. look at how mad. I'm not even gonna be able to get this in. That's absolutely insane. Okay, but okay, let's see if we can mirror these. Not bad. That is not bad. This needs to come out a little bit, actually, though. But see, these were copied in as new components, whereas these are just in the fasteners. I wonder if I can just move them into fastener. Yeah, see, I don't know. It's just doing so many random things at this point. Fine, but let's move this. I don't know, 1, -1. Let me get the exact left. Okay, so that's 2. Okay, so that's what it needs to be. Why? Because it's actually fastened, but then these aren't. Oh, I just don't know what it's doing. That's the thing. It's like there is so much seemingly random things it's doing. I mirror these fasteners. They don't become fasteners. They become components. Okay, but when they are in the fasteners thing, so what if I just try to? I don't even know what that is. But so if I just try to move this. Oh, because that's what the joint is, I guess. But then if I try to move this guy, nothing of the sort happens. In some ways, I kind of prefer that. Regardless, I think what I'm going to do is... Okay, I'm going to... Oh, wait, but I don't want to do that. I want to save the body. Save as mesh. I'm just going to print out a bunch of these, and I'm going to print out the... just 2 of the things. Okay, so this is going to be the M16 filleted nut. Okay, and then what I want to do here is just make like a my library folder. And this is just designs that I'll probably use in the future. Okay, then here. Oh, bro. What did I call that? Did I call that nut or not? Yeah, okay. I always get nuts and bolts confused. It's like left and right. Okay. So this is going to be M16 bolt for 3D printing. I mean, I don't even really need to add that in there, but okay, so now they don't know. Oh, they do. Okay. So that seems pretty good, right? All right, so let's just make one more set. We'll have 4 sets of these. Or wait, you know what? I should just do 1 for now. And then I do want to insert. I don't even know what to call it. Look at this is a garbage one. Don't save this. We want to. Okay, well, we need both to test its fastenability. So. Oh, well, let me try to do this text thing. Okay. And then on this face, we want to do the same. And we want to, oh, fuck. Go like this. Okay, here. Okay, cool. So this is going to be in a project called Compound Gears. Okay. Man, this is tough stuff. You really got to battle this freaking program. Okay, so we're going to save this as a mesh. And this should not go in there. This should go in just here. Oh, wait, but we don't want to do that. We want to do this. Why does it minimize? Gosh, there's just so many bugs, you know. Okay, save this. Okay, so now we want to import bracket 1 and bracket 2. Okay, so that one's just slightly longer. That's the only thing, is it's 2 millimeters longer. Okay, that's good with me. I'm just going to print this out. Why isn't it showing me the... There we go. I wonder if it does any... I mean, you place everything, but like, why can't you have an optimized travel thing? Whatever. All right, let's get this thing done. Is there anything in there right now that I have to run over? I don't think so. All right, and then this will be sort of like the end of the stream because I gotta go to the gym. All right. Okay, so what do we do in this 5 hours? Pretty much nothing. The rack and pinion is cool though. I like this thing. Hopefully I can get through all of them.